Welcome, friend. Take a moment, settle in, find a comfortable space where your thoughts can softly drift, like distant starlight across the quiet night. Where are you right now? What time is it for you in this vast, spinning world? Perhaps the day is winding down, or perhaps a new dawn is gently breaking. No need to answer. Just let the questions whisper through your mind. Here, in this quiet space, we're not searching for hurried answers or chasing after certainties. We're simply going to explore, to wander through the immense, shimmering tapestry of the cosmos, allowing our minds to float freely among grand ideas, vast distances, and the gentle hum of existence. This isn't a lecture, nor is it a therapy session. It's an invitation to curiosity, a soft melody for the restless mind, a quiet companionship as you journey towards stillness, or perhaps towards a peaceful sleep. Imagine, if you will, the deepest quiet of the cosmos, a place where only light truly speaks, tracing its long, winding paths across immeasurable distances. And within this profound silence, there are objects, luminous and grand, that whisper stories of creation, of power, and of the very fabric of everything we know. These are the stars, friend, those shimmering jewels scattered across the velvet canvas of night, some of the most beautiful and profoundly inspiring things we can ever contemplate. They are not merely distant points of light. They are cosmic furnaces, alive with a violent, yet exquisitely balanced dance of energy. Deep within their fiery hearts, an incredible alchemy takes place. Through what we call thermonuclear reactions, hydrogen atoms, the simplest building blocks, are fused together under unimaginable pressure and heat, giving birth to helium, and in doing so, releasing enormous, almost incomprehensible amounts of light and energy. This is the very essence of a star's existence to shine, to illuminate the vast, dark expanse of the night sky, and to gently, or sometimes fiercely, warm any planets that might find themselves cradled in their orbit. Think of our own sun, a familiar, comforting presence in our sky. It is performing this very dance right now, sending its life-giving warmth across millions of miles to our Earth, making life here possible. But the stars are more than just cosmic lanterns. They are also the universe's great alchemists, responsible for creating the heavier elements that form much of the matter we see around us, including you, me, and everything on our home planet. This incredible feat occurs through various processes, sometimes through gentle, long-term fusion, but often through the dramatic ballet of stellar merges, where two stars collide and become one, or in the breathtaking, final act of powerful cataclysmic explosions. Imagine the raw, untamed power, yet the incredible precision of such events, forging carbon, oxygen, iron, and countless other elements that eventually become the dust of nebulae, the building blocks of new stars, new planets, and perhaps new life. It's a profound thought, isn't it? That the very atoms within your hand, within your breath, might once have been forged in the heart of a distant, exploding star. Astronomers and astrophysicists, those patient, curious souls who gaze up at the heavens and ponder its secrets, have come an incredibly long way in their understanding of how these majestic, cosmic entities operate. Their tireless observations, their intricate calculations, their quiet contemplation of the light that reaches us from across the eons, have allowed us to peel back layers of mystery, revealing the elegant mechanics of stellar life. We've reached a point where we can even, with a remarkable degree of accuracy, predict the lifespan of our own comforting sun. We can foresee the distant future when it will, in a process both grand and gentle, run out of its primary fuel, and begin its slow, majestic transformation into what we call a red giant. It's a distant thought, billions of years from now, yet the science allows us to glimpse this cosmic destiny, a soft promise of change in the ceaseless dance of the universe. Today, however, we're not just going to talk about the types of stars that are familiar to us, the ones we've come to understand through meticulous observation and theory. Instead, we're going to allow our minds to wander a little further, to contemplate stars we've never actually seen before, ones that exist only in the realm of hypothesis and imaginative, yet rigorously scientific, thought. These are the exotic stars, objects so strange and wondrous that they stretch the very boundaries of our understanding, inviting us to consider possibilities that feel almost like poetry. Can you imagine stars that are, quite literally, made of vacuum? It sounds like something from a dream, doesn't it yet? In the quiet corners of astrophysical theory, such concepts gently unfold. Imagine the universe as a vast, intricate play, and we are but humble observers, occasionally catching glimpses of its most dramatic acts. These exotic stars, these whispers of what might be, can sometimes mimic the elusive nature of black holes, those cosmic enigmas that trap everything, even light. They can even resemble dark energy, that mysterious unseen force that seems to be gently, persistently pushing our universe apart, accelerating its expansion into the cool, silent vastness. This uncanny resemblance is precisely why these hypothetical stars have become the quiet focus of many recent studies, sparking both deep curiosity and, occasionally, even some gentle debate and sensational drama in the world of physics, as brilliant minds softly contend with profound possibilities. In our journey together, we're going to softly explore all of this, allowing our thoughts to drift from the foundational physical theories that lie at the core of these grand ideas, to the wildest, most imaginative speculations that gently swirl around them. But first, before we venture too far into the truly exotic, we need to lay down a little groundwork, a gentle understanding of how stars, in general, perform their magnificent work. And in doing so, where else should we begin but with the most important star of all, the one that anchors our own existence, our guiding light, the sun. Picture the sun, not as a solid sphere, but as a colossal, shimmering orb of gas, or more precisely, plasma. It's so different from our Earth, where you can feel the solid ground beneath your feet. On the sun, you couldn't stand on its surface as you would on our planet. Its immense gravity, a force so powerful it shapes galaxies, would simply pull you down, gently but inexorably, towards its searing, dense center. So, a question might softly arise in your mind: if gravity is so strong, why doesn't the sun's own gas, its luminous outer layers, get pulled inwards, collapsing completely? It's a beautiful balance, a testament to the elegant forces at play in the universe. The answer lies in a gentle, persistent pressure, constantly pushing outward from the sun's very core, perfectly counterbalancing this relentless inward pull of gravity. The primary source of this delicate, outward push is the radiation itself, created by the very fusion reactions we spoke of earlier, deep within the core. Imagine countless tiny bursts of energy, like shimmering bubbles, constantly rising from the heart of the sun. This is the same radiation that carries light and warmth from the sun's fiery depths, traveling millions of miles to reach our Earth, kissing your skin with its gentle touch. Whether you choose to imagine this radiation as individual, ephemeral photons, tiny packets of light, or as graceful, undulating waves within the vast electromagnetic field, their journey from the core towards the outer layers of the sun creates this gentle outward push in every direction. It's like a soft, invisible breeze constantly emanating from within. This radiation pressure, while powerful enough to hold the sun together, wouldn't be quite enough to stop you, a tiny human, from falling into the sun's embrace. Yet, it is precisely exquisitely enough to prevent the sun's own gas, which is relatively light compared to a human body, from collapsing in on itself. It's a perfect self-sustaining act of cosmic defiance. This delicate, perpetual balancing act, this intricate dance between the inward pulling force of gravity and the outward pushing force of internal pressure, is a fundamental feature of pretty much all the stars we know of, all the luminous beacons we've come to understand. What truly differentiates the various types of stars, what gives each its unique character and destiny, is simply where that crucial outward pushing pressure comes from. For our comforting sun, that pressure originates, as we've explored, from the profound act of fusing hydrogen atoms into helium. It's a steady, reliable process that has sustained our star for billions of years, a constant, gentle hum of creation. But even stars, with all their immense power, have a finite supply of fuel. In the distant, quiet future, in about 5 billion years from now, our sun will gradually begin to run out of its hydrogen fuel. As this primary fuel source dwindles, the delicate balance will subtly shift. The core will begin to contract, heating up further, and the sun will enter a new phase of its life. It will expand dramatically, transforming into a red giant star, its outer layers swelling outwards, perhaps even gently engulfing the inner planets. In this new, expanded state, the sun will begin to generate its life-sustaining pressure through a different, yet equally remarkable process, the fusion of helium into even heavier atomic nuclei, like carbon and oxygen. It's a deeper level of cosmic alchemy, building more complex elements in its fiery heart. But just as hydrogen is finite, so too is the helium. Eventually, the sun will also exhaust its supply of helium and any other light elements that could possibly be used as fuel for these grand nuclear fusion reactions. At that profound, quiet point, with no more fuel to sustain its fiery heart, the sun's core will finally succumb to the relentless inward pull of its own gravity. It will begin a final, slow collapse, shrinking dramatically into a small, incredibly dense star known as a white dwarf. These celestial remnants, unlike their bustling, fusion-powered predecessors, are sometimes called stellar remnants instead of true stars, because the grand fusion furnaces within them have finally ceased their work. So, if there's no more fusion, no more fiery engine generating that outward push, where does the pressure to support these incredibly dense stellar remnants, these quiet echoes of once vibrant stars, come from? It's a beautiful question, leading us to a realm of physics that feels almost magical, a world governed by the subtle, yet incredibly powerful, rules of the very small. It turns out that gravity continues its relentless pull, compacting the gas of a white dwarf inward until it reaches an unimaginable density. At this extreme point, a new, entirely different type of pressure softly emerges, one that doesn't rely on heat or fusion, but on a fundamental principle of quantum mechanics. This is known as electron degeneracy pressure. Imagine, if you will, the electrons within the white dwarf, normally buzzing freely, now packed so tightly together that they simply cannot get any closer. They are governed by a quantum rule, the Pauli exclusion principle, which states that no two identical electrons can occupy the same quantum state. It's like trying to fit too many identical marbles into the same tiny box. They simply resist, pushing back with immense force. This electron degeneracy pressure is a purely quantum mechanical effect, a whisper from the subatomic world, and it is the same subtle, yet incredibly powerful effect that's responsible for you not being able to pass your hand through solid objects. Think of your hand resting on a table. The reason your hand doesn't just pass straight through the wood is not because the atoms are physically touching, but because the electrons in your hand are repelling the electrons in the table with an extraordinary quantum mechanical force. They simply cannot get too close to each other without an extraordinary amount of energy, creating a fundamental pushback that gives matter its solidity. In a white dwarf, this pushback is magnified to a cosmic scale, strong enough to counteract the immense pull of gravity. However, the universe, in its boundless variety, presents us with even greater wonders, some stellar remnants. The silent husks of truly massive stars are so incredibly heavy, so profoundly dense, that even the powerful electron degeneracy pressure isn't quite strong enough to fully counteract the relentless inward pull of gravity. There's a limit, a cosmic threshold beyond which even this quantum pushback is overcome. This critical boundary is known as the Chandrasekhar limit, named after the brilliant astrophysicist Subrahmanyan Chandrasekhar who first calculated it. It tells us that it's absolutely, fundamentally impossible to have a stable white dwarf that is any heavier than about 1.4 times the mass of our Sun. Think of it as the ultimate weight limit for a quantum-supported star. If a star, at the end of its life, has burned through all its nuclear fuel, exhausted its grand furnace, and its core is still heavier than this sacred Chandrasekhar limit, that core will continue its inexorable collapse inward. It will shrink, becoming even denser, compressing matter to an extreme degree until it reaches a point where an even stronger, more profound type of quantum pressure gently emerges. This is known as neutron degeneracy pressure, and as you might have softly guessed, it prevents not electrons, but neutrons from getting too close to each other. It's the same principle as electron degeneracy, but applied to the even more fundamental particles that make up the nucleus of atoms. A star that reaches this astonishing superdense state is called a neutron star. These are truly remarkable objects, representing the smallest and densest known class of stellar objects in the universe. Imagine an entire star, once, perhaps many times the size of our Sun, now compressed into a sphere no larger than a city, yet containing more mass than our entire solar system. The sheer density is almost beyond comprehension. And so, a new question might softly form in your mind: is there, then, a maximum mass that a neutron star can have while still being supported by this incredibly powerful neutron degeneracy pressure? And the answer, a quiet affirmation, is yes, there is. This time, the limit is a little higher, somewhere around 2.2 times the mass of our Sun. It's a subtle, yet crucial difference, marking another cosmic threshold. If a stellar remnant, after its long, luminous life, finds itself heavier than that 2.2 solar mass limit, the relentless inward pull of its own gravity will simply overcome even the mighty neutron degeneracy pressure. And then, well, then it would keep collapsing, infinitely, under the influence of its own gravity, until, actually, not until anything, as far as we know, at least, not with the ordinary matter and physics we currently understand. Neutron degeneracy pressure is thought to be the strongest possible pressure that ordinary matter can exert. Beyond this, there's nothing left, no known force, to prevent a sufficiently heavy stellar remnant from collapsing in on itself forever. This is the profound, enigmatic fate that might await some of the most massive stars we've observed in the universe, those truly colossal beacons that shine so brightly in their youth. From the perspective of an outside observer, someone quietly watching this cosmic drama unfold from a safe distance, These stars would eventually get so incredibly dense, so profoundly compact, that all we'd ever be able to see, all that would remain, is the silent, mysterious embrace of a black hole. It's the ultimate end, a point of no return where even light cannot escape, a silent testament to the crushing power of gravity. As we left our quiet contemplation, our minds were softly drawn to the ultimate fate of massive stars, their final, relentless collapse into the enigmatic embrace of a black hole. But before we journey further into those profound mysteries, let us gently retrace our steps back to the more familiar, the more comforting journey of stars, like our very own sun. For in understanding their more common paths, we gain a deeper appreciation for the truly extraordinary. Our sun, that steadfast companion in our sky, has been burning brightly for billions of years, a steady, reliable source of light and warmth, fueled by the graceful dance of hydrogen atoms fusing into helium deep within its core. It's a process so efficient, so perfectly balanced, that it creates the illusion of timelessness. Yet, as we delicately touched upon, even this magnificent celestial body, like all things in the grand cosmic tapestry, has a finite lifespan, a gentle, inevitable progression through its life cycle. Imagine the sun now, in its middle age, a yellow dwarf star, stable and serene. Its core, a cauldron of unimaginable heat and pressure, is where the hydrogen fusion takes place, creating that outward push, that radiant pressure that holds the star in its perfect, delicate balance against the crushing, inward pull of its own gravity. It's like a quiet, enduring tug of war, with victory gracefully held in the balance. But picture, if you will, the hydrogen, slowly, steadily, being consumed, transformed. It's like a colossal fuel tank, gradually, imperceptibly, emptying. In about 5 billion years from now, a time so vast it stretches beyond our wildest imaginings, the hydrogen fuel in the sun's core will begin to run low. As this happens, the fusion reactions will subtly slow down, and that gentle outward pressure will begin to weaken ever so slightly, with less outward push to resist it. Gravity, that tireless force, will begin to assert itself more forcefully, causing the sun's core to contract and become even denser, even hotter. This contraction, a new stage in its life, will ironically ignite a fresh wave of fusion in a shell of hydrogen just outside the now exhausted core. This new, more intense shell burning will cause the sun's outer layers to expand dramatically. Imagine a once compact, glowing sphere slowly, majestically, swelling outward like a colossal cosmic balloon. Its surface temperature will cool, causing its light to shift towards the red end of the spectrum, transforming our familiar yellow sun into a red giant star. This expansion will be so vast, so profound, that it is expected to gently envelop the orbits of Mercury, Venus, and possibly even our own Earth. Picture our blue planet, once warmed from afar, now gently consumed by the ever-growing, soft red embrace of its parent star. It's a distant, yet beautiful and inevitable cosmic transformation. Within the core of this newly formed red giant, as it continues to contract and heat up, something new will begin. The helium, which was the ash of the previous hydrogen fusion, will now reach temperatures and pressures sufficient for its atoms to begin fusing. This is the next stage of stellar alchemy, the fusion of helium into even heavier elements, primarily carbon and oxygen. It's a second act, a new source of energy, extending the star's luminous life for perhaps another billion years or so. The star now supports itself through this new, deeper fusion, maintaining its inflated, red giant form. But just like the hydrogen before it, The helium fuel in the core of this red giant will also eventually dwindle. The star has, in essence, used up its lighter, more easily fused elements. There are no more readily available, simple fuels to sustain the grand, outward-pushing fusion reactions that define a star's active life. At this point, the star has reached a profound crossroads, its luminous journey nearing its gentle conclusion. With no more fusion to generate the internal pressure, gravity will once again begin its relentless inward pull. The outer layers of the red giant, now loosely bound, will gently drift away, expanding outward into the vastness of space, forming what we call a planetary nebula. These are not related to planets, despite their name, but are instead beautiful, ethereal shells of gas, often resembling cosmic bubbles or intricate, shimmering flowers illuminated by the dying ember at their center. These nebulae are fleeting cosmic artworks, lasting only for a few tens of thousands of years before gently dissipating into the interstellar medium. And what remains at the heart of this expanding, colorful cloud, the core of the once magnificent star, this core will continue to collapse under gravity, shrinking to an incredibly small, extraordinarily dense object known as a white dwarf. It will be about the size of Earth, yet contain the mass of our sun. Imagine squeezing something as vast as the sun into something no larger than a city. The density is almost unfathomable. These white dwarfs are often referred to as stellar remnants, for they are no longer actively fusing elements in their core. They are, in a sense, the gentle, dying embers of what were once vibrant, burning stars. A question might softly arise in your mind if there's no more fusion, no more fiery furnace burning at its heart. Where does the outward pushing pressure come from to support these incredibly dense, quiet stellar remnants? How do they avoid collapsing completely under their own immense gravity? It's a beautiful enigma, leading us to a realm of physics that might seem abstract, yet underpins the very solidity of our world. The answer lies in the profound and somewhat mysterious world of quantum mechanics. As gravity continues to pull the gas of the white dwarf inward, compacting it to an unimaginable degree, the electrons within the star are squeezed closer and closer together. They are forced into a state of extreme density, a state where a new and incredibly powerful pressure softly emerges, electron degeneracy pressure. To truly grasp this, we need to think on the tiniest scales. The realm of the quantum. Imagine electrons, those tiny, fundamental particles that orbit the nucleus of every atom. They are governed by a peculiar rule known as the Pauli exclusion principle. This principle, a whisper from the quantum realm, states that no two electrons can occupy the exact same quantum state at the same time. Think of it like a cosmic rule that insists each electron must have its own unique address in terms of energy and spin. When gravity attempts to compress the white dwarf's matter even further, it tries to force multiple electrons into the same quantum states. But the electrons, adhering strictly to this fundamental quantum rule, resist. They push back with an incredibly powerful force, preventing further compression. It's not a classical repulsion, like two magnets pushing apart, but a quantum mechanical resistance to being forced into identical states. This subtle, yet immense outward pressure is what prevents the white dwarf from collapsing further. It is the same fundamental force that prevents your hand from passing through a solid wall or a sturdy table. The electrons in your hand simply cannot get on top of the electrons in the wall without an extraordinary amount of energy. In a white dwarf, this pushback is magnified to a cosmic scale, a silent, unyielding guardian against collapse. So, a white dwarf exists in a delicate, long-term balance, the relentless, inward pull of gravity perfectly counteracted by the outward push of electron degeneracy pressure. It will spend the next many trillions of years slowly cooling down, its faint light gradually fading until it becomes a cold, dark, inert lump of carbon and oxygen, a silent black dwarf. This, however, is a theoretical end state, as the universe is not yet old enough for any white dwarfs to have cooled completely into black dwarfs. Their journey is long, slow, and quiet. But the universe, in its boundless capacity for wonder, presents us with even more dramatic fates. What happens if a star, at the end of its life, is so incredibly massive that even the formidable electron degeneracy pressure cannot hold against its immense inward pulling gravity? There is a threshold, a critical limit to the mass a white dwarf can have and still remain stable. This profound cosmic boundary, a whisper of destiny, is known as the Chandrasekhar limit. It states that if a stellar remnant has a mass greater than approximately 1.4 times the mass of our Sun, electron degeneracy pressure simply isn't strong enough to resist the overwhelming gravitational pull. Imagine, if you will, the Chandrasekhar limit as a cosmic weight scale. If the core of a dying star is lighter than this limit, it will gently settle into a stable white dwarf. But if it tips the scale, if its core is heavier than about 1.4 solar masses after it has shed its outer layers and exhausted its fuel, then that core will continue its inexorable rapid collapse. The electrons will be forced even closer, merging with protons to form neutrons, squeezing matter into an unimaginably dense state. This leads us to the next stage of cosmic compression, where an even stronger form of quantum pressure arises: neutron degeneracy pressure. Imagine the neutrons, now incredibly tightly packed, resisting further compression with the same quantum mechanical defiance that electrons exhibit. This force, born from the Pauli exclusion principle applied to neutrons, is even more potent than electron degeneracy pressure. A star that reaches this astonishing state, where its entire mass is compressed into a sphere just a few miles across, yet weighing more than our Sun, is called a neutron star. These are truly mind-bending objects. Imagine squeezing the mass of 1.5 suns into a sphere perhaps only 10 to 20 kilometers in diameter, roughly the size of a small city. The density of a neutron star is so extreme that a single teaspoonful of its material would weigh billions of tons. If you could transport a neutron star to Earth, its gravity would be so immense that it would rip our planet apart. The surface of a neutron star is so flat and smooth, with a surface gravity so strong that a mountain on a neutron star would be no taller than a few millimeters, and many neutron stars spin at incredible speeds, rotating hundreds of times per second, sending out precise beams of radio waves that we detect as pulsars, like cosmic lighthouses blinking in the dark. So, the question naturally softly arises in our minds once more: is there a maximum mass that a neutron star can have while still being supported by this incredible neutron degeneracy pressure? And again, the universe provides a quiet, yet profound answer. Yes, there is. This time the limit is higher, though still remarkably small by stellar standards. It's approximately 2.2 times the mass of our Sun. This is often referred to as the Tolman-Oppenheimer-Volkoff limit, or the TOV limit, named after the physicists who contributed to its understanding. This limit represents the absolute boundary for ordinary matter. If a stellar remnant is heavier than about 2.2 solar masses, even the mightiest neutron degeneracy pressure is simply not strong enough to halt the relentless, crushing pull of its own gravity. The star's core, now denser than anything we can truly comprehend, will continue to collapse. And what happens then? Well, as far as our current understanding of ordinary matter and the known laws of physics can tell us, it continues to collapse forever. There's nothing left, no known force, no quantum pushback from ordinary particles to prevent a sufficiently heavy stellar remnant from collapsing further and further, beyond the state of a neutron star, beyond any known form of matter, shrinking into an infinitely dense point. This is the profound, enigmatic fate that awaits some of the most massive stars we've observed in the universe. They burn brightly, live fiercely, and then, in their final dramatic act, they surrender entirely to gravity's embrace. From the perspective of an outside observer, someone quietly watching this cosmic drama unfold from a safe, distant vantage point, these stars would get so incredibly dense, so profoundly compact, that their gravitational pull becomes so immense that nothing, not even light itself, can escape their grasp. All we'd ever be able to see, all that would remain of their once glorious existence, is the silent, mysterious, all-consuming presence of a black hole. It's the ultimate end for stellar matter as we understand it, a cosmic void that marks the final, absolute triumph of gravity, a point of no return where the familiar laws of physics seem to bend and break, whispering secrets we are only just beginning to comprehend. This journey from hydrogen fusion to red giants, from white dwarfs supported by electron degeneracy pressure to neutron stars held up by neutron degeneracy pressure, and finally, to the ultimate collapse into black holes, paints a breathtaking picture of stellar evolution. It's a grand cosmic ballet, a slow, majestic dance of birth, life, and death, where the fundamental forces of gravity and quantum mechanics play out their roles on the grandest stages imaginable. And with each stage, the universe reveals another layer of its profound complexity and its elegant, underlying simplicity. It's a story of incredible pressures, unimaginable densities, and the relentless, yet beautiful, march of time. This understanding of how stars live and die, how their internal pressures constantly fight against the relentless pull of gravity, forms the very bedrock of modern astrophysics. It's what allows us to look up at a star like our sun and gently predict its eventual fate, to understand the shimmering remnants of distant stellar explosions, and to ponder the mysterious, unseen forces that might be at play in the most extreme corners of our cosmos. It's a comforting thought, in its own way, to know that even in the vast, cold emptiness of space, there are such intricate, predictable cycles, such profound, gentle dances playing out over billions of years. But now, having quietly laid this groundwork, having walked through the familiar landscapes of stellar evolution, our minds are ready to softly turn towards something even more peculiar, even more intriguing. We are ready to contemplate the truly exotic, the hypothetical, the stars that push the very boundaries of what we thought possible, beckoning us towards new shimmering frontiers of cosmic imagination. For what happens when the matter itself is not ordinary? What new forms might stars take, if they are not bound by the familiar pressures we've just explored? The universe, in its infinite creativity, always seems to hold another surprise, another gentle whisper of wonder, just beyond our current grasp. We have journeyed through the familiar, the grand, and the inevitable fates of ordinary stars, culminating in the profound mystery of black holes. Now, let us allow our minds to gently drift into a realm of even deeper speculation, a place where the known laws of physics are stretched, not broken, but explored in their most extreme, most imaginative corners. For scientists, those tireless seekers of truth, began to softly wonder what would happen to a star that wasn't made of ordinary matter. What if exotic, truly unusual forms of matter could hypothetically produce even larger, more profound pressures than the mighty neutron degeneracy pressure we just explored? Then, what new kinds of stars, What astonishing celestial objects could possibly exist? You might, in your quiet contemplation, naturally think that we could simply continue the pattern we were gently beginning to discern earlier. First, the white dwarf, supported by electron degeneracy pressure. Then, the neutron star, held up by the even stronger neutron degeneracy pressure. So, it would seem logical that stars could get even smaller, even denser than neutron stars, as long as they were supported by some even greater, more exotic pressure. Perhaps, you might imagine, the only limit on how small these stars could get would be that ultimate point of no return, that final threshold where they would inevitably transform into black holes. This intuition, this soft whisper of understanding, is almost true, but not quite. It's a subtle distinction, yet a profoundly important one in the realm of extreme gravity. In 1959, a brilliant physicist named Hans Adolf Buchdahl, in his quiet, meticulous work, showed something remarkable. He demonstrated that a star made of any realistic form of matter with positive energy density and positive pressure, the kind of matter we are familiar with, simply cannot be smaller than 98 times its Schwarzschild radius. Let us gently unpack what this means. The Schwarzschild radius is a critical boundary, a theoretical sphere around any mass, within which, if all the mass were compressed, it would inevitably become a black hole. It's the point of no return for light itself. For a given mass, the Schwarzschild radius defines the size of the event horizon of a black hole. So, if a star were to become a black hole, its entire mass would be compressed within this radius. Buchdahl's insight, however, reveals a subtle, yet crucial difference. That factor of 9.8, seemingly small, means that any realistic star, any star made of the matter we understand, has to be noticeably larger than a black hole of the same mass. It's like a gentle, cosmic buffer zone. This seemingly small difference, this subtle factor, makes it much, much easier to tell them apart. A black hole, by definition, is defined by its event horizon at the Schwarzschild radius. A star, even a supercompact one, would still have a physical surface outside that radius. This distinction is vital for astronomers, allowing them to differentiate between a true black hole and an incredibly dense yet still stellar object. And that, friend, is when physicists, those curious minds always pushing the boundaries of knowledge, began to softly ask about stars that Buchdahl himself might have called less realistic. What if, they pondered, a star was made of matter that allowed for pressure to be negative in some regions and positive in others? What if the very fabric of its internal forces was not uniformly pushing outward, but sometimes gently pulling inward in such a hypothetical scenario? Buchdahl's limit, that gentle cosmic buffer, would no longer apply. And if it didn't, then such a star could, theoretically, be less than 9.8 times its Schwarzschild radius. In fact, it could be arbitrarily close to the size of a black hole with the same mass, a cosmic mimic, almost indistinguishable from the outside. As a quiet aside, these theoretical stars, these cosmic doppelgangers that could mimic the appearance of black holes, came to be quite a gentle nuisance for astrophysicists. Imagine the quiet frustration. Every time they discovered something that they, in their hearts, believed was a black hole, they couldn't simply declare it so with certainty. They had to qualify their statements, softly acknowledging the possibility it's either a black hole or an extremely compact object mimicking a black hole. Even though, in their heart of hearts, most of them were quite convinced that it was indeed a black hole. The scientific rigor demanded this careful, gentle caveat. It's a testament to the cautious, questioning nature of scientific discovery. But let us gently return to our main point, to the heart of these exotic possibilities. What would these peculiar stars with negative pressures even look like? What strange internal landscapes would they possess? The answer, it turns out, is even weirder, even more profoundly unexpected than you might have softly guessed. In the 1930s, three brilliant minds, Tolman, Oppenheimer, and Volkoff, quietly derived an equation that describes how the pressure of a stable star changes as you move outward from its center. These days, in a nod to their profound contribution, it's simply called the TOV equation for short. This equation, a fundamental pillar of general relativity applied to stars, holds a fascinating secret when negative pressures are considered. If the very center of a star were to possess a significantly negative pressure, something that would exert a subtle, attractive pull instead of a gentle, outward push, the TOV equation whispers a strange and beautiful possibility. It says that such a star could only be stable, could only remain in delicate balance with its own immense gravity, if its internal pressure behaved in a truly wonky, almost paradoxical way. First, the pressure would have to somehow blow up to negative infinity somewhere within the star, a point of unimaginable inward pull. Then, in a cosmic flip, it would have to instantaneously reverse sign, soaring to positive infinity, a point of unimaginable outward push, and then gently decrease outwards from there, finally reaching zero pressure, which would mark the star's outer surface. Imagine this internal landscape, a point of infinite inward pull, then infinite outward push, all within the heart of a star. It's a concept that stretches our classical intuition to its very limits. However, the exact location of this infinite pressure, this cosmic singularity within the star, depends delicately on what the pressure is at the very center. And here lies the profound elegance. If you tune that central pressure just right, with exquisite precision, you can keep the pressure finite, well-behaved, right up until the very edge of the star, avoiding those internal infinities. This special, exquisitely tuned case occurs when the pressure at the center of the star is exactly equal in magnitude and opposite in sign to the star's energy density there. Imagine a perfect, delicate counterbalance. In this unique, profound scenario, the TOV equation whispers an even more astonishing secret. The pressure and energy density remain constant, equal in magnitude, and opposite in sign throughout the entire volume of the star, right up until its surface. It's a state of perfect internal equilibrium, a cosmic stillness within. If you've gently explored some of the other cosmic journeys we've taken together, this might softly ring a bell or two. A constant, positive energy density paired with a constant, but negative pressure. That doesn't sound like any star we've ever seen before, does it? It doesn't fit the familiar pattern of our sun or a neutron star, but it is beginning to sound remarkably, profoundly like a mysterious, elusive component of our universe, a force that permeates all of space and seems to be gently, persistently pushing the cosmos apart, dark energy. And since the pressure and energy density in this hypothetical star are not just of opposite signs, but precisely equal in magnitude, it's not just any kind of dark energy. These are the exact, precise properties of vacuum energy, the energy inherent in empty space itself. This profound resemblance, this deep theoretical connection, is precisely why this special, exotic star came to be known as a gravitational vacuum star, or gravistar for short. It's a star, yet it's made of the very fabric of empty space, a cosmic paradox. The internal landscape of a gravistar is even more mind-bending, more profoundly serene. Inside a gravistar, the TOV equation whispers, there is precisely zero net gravitational force. Imagine that. How can something so massive exert no net pull within its own boundaries? It's because the positive energy density, which typically exerts a gravitational pull, and the negative pressure, which exerts a gravitational push, perfectly cancel each other out. They are an exquisite, delicate balance, a cosmic stillness. And since the pressure within gravastars is constant throughout, there is no pressure gradient to exert any sort of push or pull in one direction or another either. This means that if you, in your quiet contemplation, could somehow find yourself gently floating inside a gravastar, you would neither be pulled inward by gravity nor pushed outward by pressure. You could simply float freely, serenely, just as though you were in a real, perfect vacuum. It's a profound thought, a place of cosmic calm at the heart of immense mass, a quiet, ethereal sanctuary. Another curious, deeply intriguing feature of these hypothetical stars with negative pressures is this: the closer you get to that special, exquisite limit of a gravastar, which, if you recall, is when the infinite pressure surface gets pushed out perfectly to the very edge of the star, avoiding any internal singularities, the more their size approaches that of a black hole with the same mass, they become almost indistinguishable from the outside, cosmic twins in their external appearance, yet profoundly different in their internal structure. This remarkable similarity, this cosmic mimicry, raises two key questions that have recently, and quite intensely, captured the quiet attention of physicists around the world. First, how can we possibly tell whether the extremely compact, incredibly dense objects that astronomers have observed in dramatic merger events, those cosmic collisions, and at the very centers of large galaxies, are truly black holes, those ultimate gravitational traps, or simply these exotic stars, these gravastars, with nearly the same size and external appearance? It's a profound challenge, a cosmic riddle. And second, an even grander, more sweeping question: if gravastars are real, if they are indeed scattered throughout the entire vast universe, could they, in their quiet, pervasive existence, be the very dark energy that's been making the universe accelerate its expansion for the past 5 billion years? Could these strange vacuum-filled stars be the unseen force gently pushing the cosmos apart, driving its ever-accelerating expansion into the cool, silent vastness? It's a truly breathtaking possibility, connecting the smallest, most extreme objects to the grandest, most mysterious forces shaping the entire cosmos. To begin to answer the first question, the one about distinguishing black holes from their exotic mimics, physicists gently rely on the main, defining distinction between black holes and other compact objects: the profound, absolute existence of an event horizon. You see, the defining, unyielding feature of a true black hole is that nothing, absolutely nothing, not even light, that falls inside its event horizon, or even gently touches its surface, can ever come back out. It's a one-way cosmic gate, an ultimate prison of gravity. On the other hand, if an exotic star, like a gravastar, is even slightly, infinitesimally larger than its Schwarzschild radius, that critical boundary, it would, by definition, not possess an event horizon. And crucially, if it doesn't have an event horizon, it would potentially be able to emit information outward, perhaps in the subtle form of light or other particles, however faint. This tiny difference, this subtle ability to communicate, is a profound distinction. Not only that, but theoretical calculations whisper another possibility. Objects without event horizons could have subtly different signatures in their gravitational wave emissions than those of true black holes, especially during a dramatic merger event, when two such colossal objects collide and coalesce. This subtle difference in the ripples of space-time could, in theory, allow us to tell them apart. We could measure and analyze those gravitational waves, those gentle cosmic tremors, using incredibly sensitive observatories like LIGO and Virgo, those silent listeners to the universe's most dramatic whispers. But even with this battery of ingenious tests, this array of subtle measurements, it turns out that sufficiently small and incredibly dense stars, those cosmic mimics, can still be remarkably difficult to distinguish from true black holes. The universe, in its elegant complexity, sometimes enjoys playing subtle tricks. So far, the best we can do is to softly state that the radius of the black hole candidates we observe in the universe is at least approximately equal to their Schwarzschild radius. In some cases, that's just a rough estimate, a gentle approximation. But in others, with incredible precision, we've calculated that radius to within an astonishing 40 decimal places, a testament to the power of our observations and theories. As for the second question, the grand sweeping one about dark energy, that's where things have recently gotten really heated, where the quiet contemplation has given way to spirited, yet respectful, scientific debate. In early 2023, an analysis led by physicists at the University of Hawaii quietly revealed a fascinating, almost startling observation. They found that astronomical observations of massive black holes, those cosmic behemoths at the centers of galaxies, showed them to be growing in mass over time at exactly the same rate that dark energy would be expected to grow over time due to the expansion of the universe. This correlation, this unexpected alignment, led them to an almost inevitable, yet highly controversial conclusion that black holes must be, in some profound sense, made of dark energy, and that they are really more like gravastars than ordinary black holes with infinite density singularities at their centers. Imagine the implications, the very voids of space-time, those ultimate gravitational traps, might actually be filled with the mysterious force that is pushing the universe apart. This conclusion, as you might imagine, was fiercely tested, met with both intrigue and skepticism. Astronomers came out gently arguing that the analysis of the observational data might not have been quite right, that there could be subtle biases or alternative explanations, and theoretical physicists, in their quiet corners, argued that the expansion of the universe, a global phenomenon, should have nothing to do with the growth of individual black holes, which are local gravitational objects. The debate, a testament to the scientific process, continues, a gentle, persistent search for truth. So, while the idea that dark energy could exist in the form of gravastars, those intriguing vacuum stars, sounds incredibly exciting, incredibly profound, it looks like the scientific community isn't going to be fully convinced unless it's simultaneously supported by better, more precise data and more compelling, more robust theoretical models. It's a high bar, a demanding path, but that is the nature of true scientific discovery. But where do you, in your quiet contemplation, fall in this fascinating debate? If an object walks like a black hole, if it talks like a black hole, if it mimics its external appearance almost perfectly, should we just call it a black hole, accepting the familiar explanation? Or should we gently consider the profound, mind-bending possibility that what we perceive as black holes could really be secret troves of dark energy, those silent, pervasive forces that shape the very destiny of our cosmos? It's a question that invites deep thought, a gentle challenge to our assumptions. Let us know your thoughts and questions, if you wish, in the quiet space of your own mind. Having gently explored the theoretical whispers of gravastars and the profound debate surrounding their potential mimicry of black holes and their connection to dark energy, let us allow our minds to drift back towards objects that we can observe, stars that, while still mysterious, offer tangible data for our telescopes to gather, and among these, few are as captivating or as perplexing as Betelgeuse. If you're a long-time admirer of the cosmic ballet, you'll already know that Betelgeuse is no ordinary star. It is a red supergiant, a colossal, luminous titan nestled within the familiar constellation of Orion, that majestic hunter in our winter sky. Though it lies a significant distance from us, some 650 light-years away from our solar system, its sheer size and brilliance make it a truly prominent fixture in our heavens. It proudly stands as the second largest star we know of, and if we gently set aside our own comforting sun, it shines as the 10th brightest star in the entire night sky. Imagine its grandeur, its immense, shimmering presence, even from such a vast remove. A few years ago, Betelgeuse quietly made headlines, drawing the curious gaze of astronomers and skywatchers alike, when this magnificent supergiant appeared to be subtly getting dimmer. This gentle fading was a source of great intrigue, sparking whispers and exciting speculation that it might be on the verge of its ultimate dramatic act exploding in a supernova, a cosmic crescendo that would briefly outshine an entire galaxy. Such an event would be a once-in-a-lifetime spectacle, a breathtaking, celestial firework, visible even in broad daylight. The anticipation, the quiet hum of scientific wonder, was palpable as everyone watched, holding their breath for this potential cosmic show. But Betelgeuse, in its majestic mystery, had another surprise gently tucked away for astronomers, a secret far more subtle, yet equally profound, than a mere dimming. Measurements gathered from the ALMA array of telescopes, a network of incredibly sensitive radio antennae, patiently listening to the whispers of the universe from a high desert plateau, detected something truly mind-bending about Betelgeuse. It appeared to be rotating at an astonishing rate. Now, when you hear mind-bending rate, you might imagine something incredibly fast, dizzying even. And for a star the size of Betelgeuse, it is. The measurement suggested it was completing one full rotation in, well, just about once every 20 years. 20. Okay, that might, at first whisper, sound a little underwhelming, perhaps even slow, especially when we consider the dizzying spin of our own Earth, completing a rotation in a mere 24 hours. But for a star of Betelgeuse's colossal proportions, a star so vast it would easily envelop our entire inner solar system and nearly reach Jupiter's orbit if placed where our sun is, this means something truly extraordinary. It means that its surface, that swirling, turbulent outer layer, is spinning at an incredible speed of about 18,000 kilometers per hour, or roughly 5 kilometers per second. To put that into a gentle perspective, that's 10 times faster than our own leisurely velocity on the surface of Earth as our planet spins. And for a star as incredibly massive and immense as Betelgeuse, a supergiant of its stature, such a speed all but gently breaks the known laws of physics as we understand them. It's a cosmic paradox, a quiet challenge to our assumptions. Imagine the universe as a vast, intricate clockwork with countless gears and cogs, each turning at its own precise rate. When something doesn't quite fit, when a gear seems to be spinning too fast or too slow, it invites us to look closer, to seek a deeper understanding. The mystery of Betelgeuse's seemingly impossible rotational speed is one such invitation. Let's gently begin with the basics. How we measure the gentle whirl of objects in the quiet, expansive night sky. There are a couple of different ways to observe and calculate the rotation of these distant celestial dancers. If the object is large enough and close enough, like our familiar sun or the serene moon, or even a planet within our own solar system, such as Jupiter, it's quite easy, quite direct. You can simply point a telescope at it, and patiently watch its visible features, its spots, its clouds, its subtle markings as they slowly, majestically move across its surface in real time. For a gentle reference, consider the angular diameter of the moon, how big it appears in our sky. It's about half a degree, a substantial visual presence, and you can probably make out its craters and seas quite clearly with your own eyes, even without aid. Jupiter, though much larger in actual size, is considerably farther away, so its angular diameter comes in at about 1/100th of a degree. Still, its swirling cloud bands and the majestic great red spot are clearly visible through even a modest telescope, revealing its stately rotation. But what about Betelgeuse? This magnificent red supergiant, despite its immense actual size, is still incredibly far away from Earth, some 650 light-years, as we softly noted. This vast distance means that its angular diameter, how big it appears in our sky, is a staggering 1,000 times smaller than Jupiter's. Imagine trying to discern details on something so incredibly distant, so incredibly small in its apparent size. It makes Betelgeuse look like a total blur, a mere smudge of light, even to our most powerful and sophisticated telescopes. Directly observing its features moving, like watching a spot on the sun, is simply impossible. The quiet blur of distance hides its secrets. Luckily, however, the ingenuity of human curiosity finds other ways. There's another, more indirect, yet incredibly clever technique to tell whether a star like Betelgeuse is gently spinning. It's less direct than simply, well, looking at it, but it's an ingenious approach that relies on a simple, familiar effect. One you might have already softly heard about: Doppler shift. Imagine, if you will, the sound of an ambulance siren. As the ambulance rushes towards you, the siren sounds higher pitched, doesn't it? Then, as it passes by and recedes into the distance, the pitch gently drops, becoming lower. This familiar phenomenon is the Doppler effect at work. When the ambulance is moving towards you, the sound waves it emits are compressed, squashed together, causing them to hit your ear at a higher frequency. This higher frequency translates into a higher pitch, but as soon as the ambulance starts moving away from you, the effect reverses. The sound waves are stretched out, pulled apart, causing them to hit your ear at a lower frequency, and thus a lower pitch. It's a subtle, yet profound, change in the very fabric of the sound waves. What you probably wouldn't notice, because it's far too subtle for our everyday senses, is that the Doppler shift affects light waves bouncing off the ambulance just like it affects the sound waves coming from its siren. As the ambulance approaches, the light waves are subtly compressed, shifting to a slightly higher frequency. For visible light, higher frequencies are perceived as bluer light. So, the ambulance would look ever so slightly bluer. And as soon as it starts moving away from you, the effect flips. The light waves are stretched, shifting to a slightly lower frequency, which for visible light makes it look ever so slightly redder. The only reason this visual effect isn't obvious to us in our daily lives is because the speed of light is so incredibly, unimaginably fast, 1,000,000 times faster than the speed of sound. So, it would take an ambulance moving at utterly inconceivable speeds far beyond anything terrestrial, for us to actually notice this optical Doppler shift with our naked eyes. We might not have ambulances here on Earth flying by at 5 kilometers per second, the speed we suspect for Betelgeuse's surface, but those kinds of speeds, those cosmic velocities, are fair game out in the vast, open expanse of space. And this, friend, brings us gently back to the mystery of Betelgeuse. When a star is rotating, 1/2 of its colossal surface will be moving towards us, gently spinning into our line of sight, while at the very same time, the other half will be moving away, gracefully receding. This creates a subtle yet measurable gradient of colors emitted by the star that we can carefully observe with our powerful telescopes, even if the star itself is too blurry, too distant for us to make out any of its distinct features, like trying to see details on a distant, shimmering pearl. We can still detect this delicate color shift across its apparent disk. By seeing which side is subtly bluer, indicating movement towards us, and which side is gently redder, indicating movement away from us, we can softly infer the direction of the star's rotation, and by meticulously measuring how different the bluer frequencies are from the redder ones, we can, with remarkable precision, calculate the star's rotational velocity. It's an ingenious technique, a testament to our ability to deduce the unseen from the subtle whispers of light. This was precisely the sophisticated technique used by astronomers to carefully analyze the vast amounts of data collected by the ALMA array, allowing them to gently conclude that the surface of Betelgeuse was, indeed, spinning at an astonishing 5 kilometers per second. It was a groundbreaking measurement, a profound revelation, and yet it immediately presented a perplexing challenge to our deepest understanding of stars. You see, the known physics of spinning stars, the elegant equations that describe their behavior, gently predict that 5 kilometers per second is far too large a velocity for a red supergiant like Betelgeuse. It's like discovering a colossal, majestic whale gracefully swimming at the speed of a cheetah. It simply doesn't fit our current understanding. Consider our own sun, for a moment, a much smaller, lighter star. Its rotational speed at its equator is a mere 2 kilometers per second, a much more sedate pace. Yet, Betelgeuse is 1,000 times larger in diameter and about 10 times heavier than our sun. Think about the principle of conservation of angular momentum. It's like a spinning ice skater. When she pulls her arms in close to her body, she spins faster, but when she gracefully spreads her arms out, her rotational speed gently slows down. The same principle applies to stars. If our sun were to expand to the colossal size of Betelgeuse, a transformation that would, as we imagined, envelop the entire inner solar system and nearly reach Jupiter's orbit in the process, then, in order to conserve its angular momentum, its rotational velocity would dramatically drop to a mere 2 meters per second. That's incredibly slow, barely a gentle crawl. And if the sun were to grow 10 times heavier, to match the immense mass of Betelgeuse, its velocity would drop even further to a gentle 0.2 meters per second. So, the larger and heavier a star is, the slower we naturally expect it to spin, and yet, Betelgeuse, in its cosmic defiance, appears to defy all of these gentle expectations. It stands as a profound anomaly, a silent, swirling riddle in the night sky. What could possibly be going on here? This cosmic paradox, this puzzling discrepancy, has led scientists to softly propose several intriguing explanations, each a testament to their boundless curiosity. One possible explanation, a dramatic and fascinating one, is that even though Betelgeuse didn't begin its life with this much angular momentum, this innate cosmic spin, it gained it through a spectacular process known as stellar cannibalism. Imagine, if you will, a cosmic dance of two stars in a close embrace. Stellar cannibalism, as the name gently suggests, is precisely what we call it when one star, typically a larger, more massive one, begins to gravitationally draw in to slowly eat another star, usually its smaller, less massive companion in a binary orbit. In more scientific yet still gentle terms, the larger star's immense gravity subtly pulls away its companion's gas layer by layer, like peeling away the delicate skin of an onion, until only the dense inner core of the companion might remain, or it is entirely consumed. This devoured gas, this stolen stellar material, carries with it most of the companion star's inherent angular momentum. its original cosmic spin. So, the first, larger star ends up not only growing immensely larger in size, but also, crucially, spinning much faster than nature would normally allow for a star of its final, immense mass. It's like an ice skater suddenly grabbing another skater, absorbing their spin, and accelerating to a dizzying rate. But is this dramatic tale, this cosmic feast, really the story of how Betelgeuse acquired its astonishing spin, or is there something even more mysterious, more subtly veiled, happening beneath its turbulent, shimmering surface? The universe, in its quiet wisdom, often holds many secrets. As we gently ponder the intriguing possibility of Betelgeuse having consumed a companion star to acquire its seemingly impossible spin, let us now consider an alternative explanation, one that whispers of an even more subtle cosmic deception. What if, instead of a dramatic act of stellar cannibalism, Betelgeuse's apparently ludicrous rotation speed is, in fact, nothing more than a giant optical illusion? This idea, proposed by a team of patient and insightful researchers collaborating across Europe and China, invites us to question what our telescopes truly see and how we interpret the subtle whispers of light from distant stars. To truly grasp how such an illusion might be possible, let us gently revisit what the ALMA team, with their state-of-the-art array of telescopes, truly measured. Their images of Betelgeuse, while groundbreaking, were still, by their very nature, quite blurry. The immense distance to the star, as we have explored, turns even the most majestic supergiant into a mere smudge of light. Yet, despite this blur, they were able to discern something crucial. One half of the star appeared to emit slightly redder frequencies of light than normal, while the other half emitted slightly bluer frequencies. It was this subtle, consistent 50-50 split in color that formed the basis for their conclusion. The obvious, and indeed most straightforward, explanation for this consistent color gradient is precisely what was inferred, that the star is rotating, with one half of its colossal surface moving towards us, causing a blue shift, and the other half moving away from us, causing a red shift. Imagine a vast, spinning sphere, with one side approaching and the other receding, painting a beautiful, predictable spectrum across its face. The green arrow often seen in the image of Betelgeuse, gently bisecting its disk, is meant to visually represent the axis of this inferred rotation, the pivot around which this cosmic dance supposedly takes place. But what if, the researcher softly mused, that isn't the only explanation for the color gradient detected by ALMA? What if the universe, in its intricate complexity, has another, more subtle trick up its sleeve? This is where the true nature of Betelgeuse's surface comes into play. Simulations, those digital whispers of what might be, have revealed that the surface of Betelgeuse is a chaotic, turbulent place, not a serene, smoothly spinning orb. Imagine a colossal, cosmic pot of boiling water, constantly bubbling and churning under its own immense heat. Each of these bubbles on Betelgeuse's surface is truly enormous, propagating outwards with deadly, yet majestic, velocities. A single one of these convective cells, these cosmic bubbles, can be a staggering 100 million kilometers across, covering a large fraction of the supergiant's entire surface. To put that into a gentle perspective, that's larger than the distance between our Sun and Mercury. And if one of these colossal bubbles were headed your way, even today's most powerful and advanced spacecraft wouldn't save you from its incredible, light-fast speed, which can reach up to 30 kilometers per second. It's a testament to the raw, untamed power bubbling beneath a supergiant's surface. Your only hope in such a dire hypothetical scenario would be for the bubble to gracefully pop and crash violently back down onto the surface before it ever reached you. As these immense gas bubbles all over Betelgeuse's surface continually rise and fall, creating a dynamic, ever-changing landscape. Its outer layers become a mosaic, a complex patchwork of regions that are either subtly moving towards us as they rise, or gently moving away from us as they fall back down. In turn, the relentless, yet subtle, Doppler shift causes the light emitted from these regions to be either blue shifted from the rising parts or red shifted from the falling parts. It's like a constantly shifting quilt of colors, each patch subtly betraying its motion. In a recent paper, a quiet yet profound challenge to all previous explanations of Betelgeuse's seemingly impossible rotation, this international team of researchers proposed a revolutionary idea. What if Betelgeuse isn't rotating fast at all? What if, instead, the ALMA observations, those careful measurements of light frequencies, are merely detecting the subtle range of light frequencies coming from Betelgeuse due to the intense turbulence on its surface? This means that astronomers, with all their meticulous analysis, may have been gently misinterpreting those shifts in frequency, those subtle changes in color, as a grand rotational effect, when they were in fact witnessing the internal turmoil of a gigantic, bubbling star. It's a compelling thought, shifting our perspective from global spin to local chaos. But if you've been paying close attention to the subtle whispers of physics we've explored, a gentle loose end might still linger in your mind with this alternative explanation. A truly rotating star, as we discussed, should produce a smooth, continuous gradient of light frequencies, ranging from bluer than expected light on one edge to redder than expected light on the opposite edge. It's a graceful, predictable spectrum across the star's face. Meanwhile, a turbulent star, with its chaotic, bubbling surface, should produce a more random, unpredictable patchwork of colors, with bluer patches appearing where bubbles happen to be rising towards us, and redder patches appearing where bubbles happen to be falling back down. How, then, could the astronomers at ALMA possibly have mistaken one for the other? If astronomers observed a smooth gradient of colors coming from Betelgeuse, shouldn't the patchwork explanation, the idea of surface turbulence, already be ruled out? In an ideal world, a perfect, unblurred vision of a distant star, that would indeed be true. Smooth gradients would unequivocally correspond to rotation, and distinct, chaotic patches would unequivocally correspond to bubbling turbulence. But remember, friend, that Betelgeuse is so incredibly far away. The image captured by ALMA, though technologically wondrous, is far from ideal. It's more of a blur, a soft, indistinct smudge of light, rather than a perfectly sharp, high-definition photograph. This crucial limitation, this inherent blurriness of extreme distance, holds the key to the illusion. When simulations, those digital recreations of cosmic reality, are made to account for the limited resolution of our observations, when they are deliberately blurred to mimic what ALMA actually saw, they whisper a surprising truth. These simulations predict that the bubbly patches of redshift and blueshift, those chaotic individual motions on the star's surface, will, in fact, be easily mistaken for a smooth, continuous rotational gradient about 90% of the time. Imagine the gentle deception, the chaos of boiling, when seen through a blurry lens, appears as a smooth, majestic spin. This means that even if the astronomers at ALMA did absolutely nothing wrong in their meticulous analysis, even if their calculations were perfectly sound, they may have been subtly fooled by Betelgeuse's boiling, turbulent surface into thinking it's spinning way faster than it actually is. It's a beautiful example of how the universe, even in its most dramatic displays, can offer a subtle illusion. This profound realization, this new whisper of a possibility, means that astronomers are now gently chasing after one key objective: One crucial piece of the puzzle, higher resolution studies of Betelgeuse. They are seeking clearer, sharper images that could more accurately tell the two scenarios apart. The graceful, yet impossibly fast, spin, or the chaotic, yet deceptively smooth-looking, surface turbulence. The good news, for those of us who patiently await cosmic revelations, is that better images of Betelgeuse already exist. They were taken by the very same ALMA telescope, but with longer exposure times, allowing more light to be gathered, more detail to be resolved, like letting your eyes adjust to the subtle nuances of a painting. The less comforting news, for those of us who are more impatient for cosmic answers, is that it will likely take a couple of years for these new, richer data sets to be properly analyzed. The process of extracting information from such vast, complex astronomical data is meticulous, painstaking, and requires immense computational power and human ingenuity. Those answers are coming, though slowly, patiently, like the tide turning. For now, in this quiet moment of contemplation, I'm curious to know where you, in your own thoughts, would place your bets. Is Betelgeuse truly spinning at an astonishing 5 kilometers per second, a dizzying remnant after having perhaps devoured its companion star in a spectacular act of cosmic cannibalism? Or will the new claim that this incredible rotation speed is nothing more than a magnificent optical illusion caused by its boiling, turbulent surface be vindicated by the patient work of astronomers? Let these thoughts gently swirl in your mind, a cosmic riddle to ponder as you drift. We have gently unwound the mysteries surrounding Betelgeuse's perplexing spin, contemplating both the dramatic tale of stellar cannibalism and the subtle illusion of a turbulent surface. Now, let us allow our minds to float towards another spectacular celestial event, one that offers a profound glimpse into the dynamic lives of stars, and surprisingly, is poised to grace our skies once more. Have you ever, in your quiet moments of cosmic dreaming, wished you could see a supernova up close, while we don't quite expect that in the coming year? 2024, you will have a remarkable chance to witness what is arguably the next best thing, the magnificent explosion of a star known as T Coronae Borealis, affectionately nicknamed the Blaze Star. And intriguingly, this particular star just keeps exploding over and over again, like a cosmic firework set to a grand 80-year timer. Let us gently rewind the cosmic clock to a particular spring night, May 8th, 1866. On a partly cloudy evening in the west of Ireland, an amateur astronomer named John Birmingham was quietly making his way home in the dark just before midnight. His pace, perhaps, slowed occasionally, allowing him to tilt his head back and look up at the familiar constellations, a ritual he had performed countless times before. As his eyes, sharp and practiced, reached the constellation known as the Northern Crown, a small, graceful semicircle of stars, he stopped, stunned. There, shining brightly, was a new, brilliant star in this familiar celestial diadem, a star that had not been there before. He had, with his own careful observation, witnessed a recurring nova in the binary star system T Coronae Borealis. This event, now affectionately dubbed the Blaze Star, was an explosive astronomical spectacle, a true once-in-a-lifetime occurrence for any single observer. This singular event would, in its quiet power, help to revolutionize our understanding of nova events and profoundly shape the field of stellar astronomy in the decades that followed. And for those of us alive in this present moment, in 2024, we will have the unique, profound opportunity to experience the very same recurring nova explosion that so captivated John Birmingham's imagination more than 150 years ago on that cool spring night in Ireland. Imagine the connection, the shared sense of wonder across generations, linked by a single distant star. And the most comforting part, you won't even need a powerful telescope or any fancy equipment to see it. It will be a gift from the cosmos, visible to the unaided eye, if you know where to look. So, the gentle question arises, why is it going to happen again? And when, precisely, will it grace our skies? These are the secrets the blazed star holds, and we shall gently unveil them. The nickname blazed star, while evocative, can be a little misleading. It's not a solitary star, but rather a magnificent binary system of two stars, two celestial companions locked in an intricate, eternal orbit with each other. And it is the profound, delicate, and sometimes dramatic relationship between these two stars that is the very cause of the nova explosion, occurring reliably, beautifully, about once every 80 years or so. It's a rhythmic, cosmic heartbeat. In fact, it's estimated that about 50% of the stars we gaze upon in the night sky are not solitary, but are actually part of multiple star systems, quietly dancing together in the cosmic dark. Both of the stars within the blazed star system began their luminous lives as average-sized stars, quite similar in mass to our own comforting sun. However, in their long, evolving journey, each one finds itself at a very different, distinct stage in its life cycle. Small and mid-sized stars, like our sun, generally follow a similar, predictable evolutionary path. Our own sun, at approximately 4.6 billion years old, is considered a middle-aged, average-sized star, shining steadily and reliably. In about 5 billion years, as we discussed, it will gently run out of its primary hydrogen fuel and begin to fuse heavier elements, majestically expanding into a red giant. This red giant phase will be so immense that it may well envelop Mercury, Venus, and possibly even our own beloved Earth. As this red giant quietly uses up its remaining fuel, sometime between 5 to 10 billion years from now, it will eventually cast off its outer shell, like a cosmic breath, creating a beautiful, expanding nebula of gases surrounding a tiny, incredibly dense core. This core is what we call a white dwarf, the incredibly small, super-compact remnant of the once giant star. White dwarfs are often referred to as dead stars because they have no more internal fuel for nuclear fusion. They will spend the next 10 trillion years or so slowly cooling off, their faint light gradually dimming until they no longer emit any perceptible heat or light, becoming quiet, dark embers in the vast cosmic night. Now, let us turn our gaze back to the blazed star system. Both of the binary stars in this system, as we noted, are average-sized stars, following the same grand evolutionary trajectory as our sun. However, they are significantly further along in their stellar evolution. In fact, this advanced stage in their lives is the very reason, the profound cosmic setup for the recurring nova that we will be able to witness in 2024. It all comes down to the intimate, compelling relationship between these two stars, one, a gracefully aging red giant, and the other, a tiny, incredibly dense white dwarf. Imagine the red giant in its vast, expanded state, gently heating up and its outer shell subtly, constantly expanding. As it swells, its outermost layers become less tightly bound to its core. And here is where the powerful drama unfolds: the immense gravitational pull of its neighboring white dwarf. That tiny, dense companion continually strips away hydrogen-rich material from the red giant's expanding outer atmosphere. It's like a cosmic vacuum cleaner, gently, persistently siphoning gas from its larger partner. Over time, this material, rich in hydrogen, slowly, steadily, accumulates on the surface of the white dwarf. This isn't a violent, instantaneous process, but a gradual, quiet buildup, layer by layer, like dew collecting on a window pane. As the material gathers, the immense gravity of the white dwarf compresses it, causing a profound buildup of pressure and heat on its surface. Imagine the incredible weight, the growing intensity of billions of tons of gas being squeezed onto a tiny city-sized sphere. Eventually, this gentle, persistent buildup of material, this growing pressure and heat, becomes simply too much for the white dwarf's surface to contain. It reaches a critical point, a cosmic breaking point, and when it does, it triggers a sudden, violent, yet beautifully controlled thermonuclear explosion that blasts away all of that built-up material into space. Think of it, if you will, like a party popper. You keep gently pulling the string tighter and tighter, adding more and more tension, slowly building the internal pressure. Finally, you pull just hard enough. The tension reaches its limit, and it pops. Confetti and streamers fly everywhere in a sudden, joyful burst. This is somewhat akin to the pressure and heat that builds up on the Blaze Star's white dwarf. The accumulated hydrogen reaches ignition temperature and pressure, triggering a runaway nuclear fusion reaction on its surface, a powerful yet contained explosion until it finally reaches its limit, and that immense built-up material is suddenly ejected into the vastness of space. The result of this dramatic yet recurring event is a nova explosion. And what an explosion it is, so powerful, so incredibly luminous, that it can make the Blaze Star, normally too faint to be seen with the naked eye, appear an astonishing 1/500 times brighter than usual. From our vantage point on Earth, some 3,000 light years away, this sudden surge in brightness is a truly spectacular sight, occurring reliably, beautifully, about once every 80 years. It's a cosmic chime, marking a predictable rhythm in the dance of stars. So, a gentle question might arise: how is this magnificent nova explosion different from the more famous, more cataclysmic supernovas we sometimes hear about? While the Blaze Star certainly experiences a massive, powerful explosion with each nova event, often referred to as a classic nova, there's a crucial distinction. A nova does not destroy the white dwarf where it occurs. Instead, it simply blasts away the accumulated material, the hydrogen fuel collected from its neighboring red giant, allowing the white dwarf to survive the explosion relatively unscathed. It's like clearing a stage for the next act. The white dwarf remains, continuing its gravitational siphon, ready to gather more material and explode again in another 80 years or so, whenever the pressure and heat once again become too much, and it happens to be close enough to us that we will experience a significant dramatic change in its brightness from Earth. On the other hand, for a solitary star to utterly destroy itself at the end of its life by exploding in a truly grandiose supernova, a cosmic cataclysm that can be millions of times brighter than even the blaze nova, it has to start out with an immense amount of mass, typically more than 8 times the mass of our sun. These are the giants of the cosmos, far more massive than the stars in the Blaze Star system. Their internal structure and final collapse are far more violent, leading to their complete destruction. The closest star on a path towards such a dramatic supernova explosion in the relatively near future, from a cosmic perspective, is our familiar red supergiant, Betelgeuse. This colossal star often appears as one of the 10 brightest in our night sky, despite being some 640 light-years away. But by near future, we mean in cosmic terms, those vast timescales that stretch beyond human comprehension. So, do not worry. Scientists do not expect this majestic star to go supernova for tens of thousands of years, at the very least. In cosmic terms, that's just around the corner. In human terms, not so much. But just for a moment, allow your mind to gently imagine the awe-inspiring view, the breathtaking spectacle that anyone on Earth would witness if Betelgeuse were to explode in a supernova within our lifetime. After the initial brilliant flash of the explosion, the star would become as bright as a full moon, perhaps even brighter, a second sun in our sky. It would remain vividly visible even during the daytime, a constant luminous presence. What a sight that would be. A profound, humbling reminder of the universe's immense power and beauty. However, while extraordinarily rare, a supernova of this magnitude would not be the first time humanity has witnessed such a cosmic firework. And the blazed star is certainly not the only nova in recent history to be visible to the unaided eye. The oldest reliable record of a supernova, now designated SN 185, comes from ancient Chinese astronomers in 185 AD. They meticulously recorded what they called a guest star, which appeared in the night sky and remained visible for a staggering 8 months. Modern astronomers have since been able to find the subtle remnants of this ancient explosion, quietly confirming that it was, indeed, a supernova. There have only been a handful of supernovae that were visibly bright enough to be seen with the naked eye in recorded human history. One of the most famous instances, and one of the most recent, occurred in 1604 when the brilliant German astronomer Johannes Kepler meticulously documented a supernova that was so bright people could astonishingly see it even during the daytime. These rare, dramatic events are profound markers in our collective cosmic consciousness. What we will experience in 2024 with the blazed star is expected to be one of the brightest classic nova events of this entire century. And just like a supernova, this is a rare and truly noteworthy occurrence. While classic novae that are visible to the naked eye occur relatively frequently, at least compared to supernovae, perhaps about once every year or two, they are rarely bright enough for the untrained or unaided eye to spot with ease. The blazed star, on the other hand, is expected to be one of the brightest classic novae to grace our night sky in nearly 50 years. It's a special gift, a cosmic appointment. In astronomy, a star's brightness as seen from Earth can be precisely measured on a scale called apparent magnitude. This scale is a little counterintuitive, so let us gently clarify. The smaller the magnitude number, the brighter the star. So, a star with an apparent magnitude of 0 is brighter than a star with a magnitude of 1. A star with a magnitude of 1 is brighter than a star with a magnitude of 2, and so on. Typically, it takes an apparent magnitude of about 6.5 or smaller for a star or planet to be visible to the naked eye on the darkest, clearest night. To give you a gentle sense of perspective, consider the 7 stars that form the familiar ladle of the Ursa Major constellation, also known as the Big Dipper. Their apparent magnitudes range from the dimmest at 4.8 to the brightest at a magnitude of 1.7. The brightest star in our entire night sky is the brilliant Sirius, with an impressive magnitude of 1.44, and our own daytime sun, a beacon of light, has an astonishing magnitude of 26.5. Yes, the apparent magnitude scale does indeed extend into the negatives, representing extreme brilliance. The blazed star, in its usual quiet state, has an apparent magnitude of about 10. This means it is typically far too faint to be visible to the naked eye from Earth, hidden in the background of faint stars. But during its nova explosion, which recurs approximately every 80 years, this star peaks at a dazzling magnitude somewhere between 3 and 2. This dramatic shift means it will appear from seemingly nowhere to become one of the brightest stars in the night sky, a true cosmic marvel. Interestingly, the term nova itself comes from a Latin word meaning new, and I'm sure that before the invention of telescopes, it must have been an absolute shock, a profound surprise, to see a brilliant new star suddenly appear out of nowhere in the seemingly unchanging night sky. More recently, there was Nova Centauri 2013, which gently surprised astronomers by being one of the brightest in over a century, peaking at a magnitude of 3.3. the last time the blaze star erupted in its nova phase. Back in 1946, it reached a magnitude of 3, but this year's eagerly anticipated appearance of the blaze star is expected to be even brighter than that, possibly reaching a peak magnitude of 2. If it achieves this, it would brilliantly rival the brightness of Polaris, our familiar North Star, which has a magnitude of 1.97. Imagine a previously invisible star suddenly shining with the brilliance of Polaris. However, this magnificent stellar show won't last long. Once it erupts with its nova explosion, the blaze star may only be visibly bright enough for the naked eye for a few days, or perhaps a week, before it gradually, gently fades back into the darkness. Returning to its usual quiet magnitude of 10, there is no exact date when this cosmic spectacle will happen, adding to the gentle anticipation. But scientists predict it may happen any day now, as we move into the second half of 2024. So be sure to keep a soft eye on the news and, most importantly, on the night sky itself, to find out when this unique nova explosion begins. It's a cosmic appointment, a whisper from the stars. To find the blaze star in the night sky, look for the 2 neighboring constellations of Hercules, the mighty hero, and the kite-shaped Botas, the herdsman. The blaze star will be located in a small, graceful, semicircle-shaped constellation called the Northern Crown, or Corona Borealis. Nestled gently between these 2 larger, more familiar constellations. If you trace the Northern Crown, starting from the Botas constellation and ending on the side closest to Hercules, the blaze star should appear just below the last star of the Northern Crown, like a new jewel added to its ancient diadem. And if you happen to have access to a powerful amateur telescope, or can visit a local observatory, you may even be able to spot this binary star system before the nova truly begins, observing its faint, quiet presence before its grand, fiery awakening. These recurring novae, these gentle cosmic explosions, remind us that even stars, which can seem eternal and unchanging in their distant brilliance, have astonishing life cycles that can include drastic changes and dramatic explosions, like a magnificent cosmic fireworks show, rare and awesome. Each nova provides a unique opportunity for astronomers to patiently gather invaluable data that will help to refine our understanding of stellar evolution, the intricate dances within binary star systems, and the profound physics of explosive stellar phenomena. This particular nova, the blaze star, will be one of the most exciting astronomical events we will get to see in our lifetime. So, keep a gentle eye on the night sky, and perhaps feel just that little bit luckier, that little bit more connected, to be alive and to be able to experience this here on Earth. A tiny blue marble suspended in the grand cosmic dance. We have gently traversed the dramatic dance of stars, from their fiery births to their dazzling deaths, and even to the captivating spectacle of recurring novae. Now, let us shift our gaze to an even grander concept, one that encompasses all these cosmic wonders, reaching back to the very beginning of everything, the age of our universe. You have probably heard, in your quiet contemplation of existence, that modern-day science, through countless hours of patient observation and meticulous calculation, believes our universe to be approximately 13.8 billion years old. It seems a rather unfathomable figure, a number so immense it stretches the very limits of our imagination. How, one might softly wonder, could anyone possibly come to such a precise conclusion about something so vast and ancient? Actually, the how is not as difficult to grasp as it might initially seem. It is a story woven from light, from distance, and from the gentle, persistent expansion of space itself. People, in their hurried lives, don't generally ask this question, either scoffing at the audacity of such a claim or simply accepting it as a profound truth. But here, in our quiet space of exploration, we will gently delve into this how. And, as is often the case in the grand tapestry of scientific discovery, we will also softly introduce a curious anomaly, a gentle spanner in the works, in the form of a newly discovered age for one of our local stars, affectionately called the Methuselah Star, which, astonishingly, appears to be older than the universe itself. It's a cosmic riddle, a beautiful paradox that invites deeper thought. So, let us begin with the figure itself. 13.8 billion years old. How did we, as a species, come to such a precise cosmic birth date? The journey begins with a fundamental observation. We currently see the universe in a state of continuous expansion and cooling. Imagine, if you will, a vast cosmic loaf of bread baking in an oven. As it heats, it expands, and the raisins within it, representing galaxies, move further and further apart from each other, even though they aren't actually moving through the bread, but rather the bread itself is expanding. In the universe, everything is gently moving away from everything else, subtly increasing the distances between galaxies, though local forces like gravity still lovingly keep things like stars within galaxies, and galaxies within clusters, together. The speed of this grand cosmic expansion is a crucial piece of our puzzle. It is known as the Hubble constant, named after the pioneering astronomer Edwin Hubble. Currently, our universe is expanding at a gentle, yet immense, rate of approximately 80,000 kilometers per hour per million light-years of distance. Imagine that for every million light-years you look out into space, the universe is stretching away from you at that astonishing speed. It's like a gentle, ceaseless inflation of the fabric of space-time itself. The obvious conclusion from an expanding universe is that matter is becoming more and more diluted. There's more space, more gentle emptiness in between things, but a less obvious, yet equally profound result of the universe expanding is the stretching of light wavelengths, a phenomenon known as redshift. Imagine a wave on a pond. If the pond itself is stretching, the waves will become longer, more drawn out. In the cosmos, what started off as incredibly high energy, high-frequency light waves, emitted shortly after the universe's fiery birth in the Big Bang, have been stretched, lengthened, and diluted by the intervening expansion of space. By the time they finally reach us, billions of years later, they arrive as less energetic, longer wavelength microwaves, forming what we beautifully call the cosmic microwave background radiation, or CMB. This faint, uniform glow permeating all of space is like the gentle echo, the ancient afterglow, of the universe's earliest moments. It's also why the James Webb Space Telescope, that marvel of modern engineering, is primarily an infrared telescope. Light photons emitted by galaxies that are billions of light years away, traveling across the vast, expanding cosmic ocean, have had their frequencies shifted, or redshifted, so much by the expansion that they are no longer visible to our eyes. They have stretched from visible light into the infrared spectrum, which is beyond what human eyes can perceive. To observe them, to capture their ancient whispers, we need an infrared telescope capable of discerning these stretched-out wavelengths. A photon, that tiny packet of light, contains energy, and a higher frequency wavelength means more energy, which implies it is hotter. Conversely, lower frequencies mean it is less hot, cooler. Hence, we softly say that the universe was once incredibly dense and hot, a primordial soup of energy. But now, after billions of years of expansion, it is much bigger, much more diffuse, and much cooler, a gentle, silent expanse. But how, you might softly wonder, does knowing all of this, the expansion, the redshift, the cooling, help us work out the precise age of the universe? Well, to make this profound calculation, we do need to assume a few fundamental things about the universe. foundational principles that help simplify this immense cosmic equation. First, we assume that on the very largest scales, the universe is uniformly dense. This might sound wrong at first whisper, doesn't it? When we look around, we clearly see that it's not uniform. There are immense superclusters full of densely packed galaxies and vast, empty supervoids containing not much at all. But imagine, if you will, zooming out far, far enough, so far that individual galaxies become mere specks and clusters become tiny dust motes. From this immense cosmic vantage point, everything suddenly begins to look the same, smooth and evenly distributed. So, we assume the universe is homogeneous, meaning it looks broadly the same everywhere. As a gentle consequence of that, we also assume that, secondly, the universe's laws and properties are the same throughout, in any direction we choose to look, whether you look to the left or to the right, up or down, the laws of physics, the behavior of gravity, the speed of light, all remain constant. This is the assumption of isotropy. And thirdly, a profound concept. We assume that the Big Bang, that fiery, energetic beginning, occurred in all locations, everywhere, all at once. It wasn't an explosion in space, but an explosion of space itself, a simultaneous unfolding of everything, everywhere. If you hadn't heard that before, it's a concept that invites quiet contemplation. Under the elegant laws of general relativity, if these three things, homogeneity, isotropy, and a simultaneous Big Bang, are true, then there is a deep, profound connection between how old the universe is and how it has expanded throughout its long, winding history. With these fundamental assumptions as our gentle guide, we can then use various cosmic yardsticks and clocks. We can gather meticulous distance and brightness measurements between celestial objects, such as distant stars, exploding supernovae, and vast galaxies. For instance, certain types of supernovae, specifically type Ia supernovae, which result from the explosion of white dwarfs in binary systems, are incredibly useful. They always appear to have roughly the same intrinsic brightness when they explode, acting like perfect, standard cosmic light bulbs. So, if an observed type Ia supernova appears dim compared to what we expect, it's because it is incredibly far away. And by figuring out precisely how dim it is, we can calculate how far away it truly is, and thus how far back in time we are looking when we observe its ancient light. It's like reading a cosmic clock by the faintness of its glow. We can also look for subtle fluctuations in the cosmic microwave background radiation, that ancient afterglow. The CMB is a remarkable snapshot of the universe when it was only a few 100,000 years old, a tiny fraction of its current age. By carefully comparing these minute temperature fluctuations in the CMB to the large-scale galaxy clusters and supervoids we see today, we can find a profound correlation. This allows us to map out how these initial tiny ripples grew over billions of years, providing a precise understanding of how the universe evolved and expanded from its earliest moments to its current state. Based on the current rate of the universe's expansion, the Hubble constant we discussed, and by meticulously tracing how it did expand over billions of years, we have also been able to determine the precise composition of our universe. We now know, with a remarkable degree of certainty, that the universe is made up of approximately 68% dark energy, 27% dark matter, and only about 5% observable matter, the stars, galaxies, and everything we can see and touch. But what are dark matter and dark energy? Here, our gentle exploration hits a quiet boundary of current human knowledge. We really don't have much of an idea. They are profoundly mysterious. However, we can clearly see their effects, their subtle gravitational whispers on the universe. Dark energy is widely believed to be the unseen driving force behind the universe's ever-accelerating expansion. Without it, the expansion would have gradually slowed down by now due to the mutual gravitational pull of all matter. But instead, it seems to be gently speeding up. Dark matter, on the other hand, is like an unseen gravitational glue. It represents a gravitational force we simply can't account for with the visible matter. Galaxies and galaxy clusters, in particular, seem to have a lot more mass than they should, based on how fast their stars are orbiting and how much gravity is needed to hold them together. This discrepancy suggests the presence of unseen gravitational influence. Dark matter is what must gently keep galaxy filaments, those vast cosmic superstructures, together. We can observe its profound influence, its subtle gravitational fingerprints. In fact, we can even map out its mass distribution, like tracing an invisible web across the cosmos, but we don't know what it is. We can't directly observe it, only infer its powerful presence. However, for the gentle purpose of determining the universe's age, we don't necessarily need to know what dark matter and dark energy are, only what they do to the expansion of the universe. Their gravitational and expansive influences are woven into the fabric of space-time, and by understanding these influences, we can precisely trace the universe's history. So, let us recap the tools we use to gently piece together this cosmic timeline. We know the current rate of the universe's expansion, the Hubble constant. We know how that expansion causes light to stretch, leading to redshift. We have a good understanding of the composition of the universe, the percentages of dark energy, dark matter, and ordinary matter, and we understand its fundamental properties, such as homogeneity and isotropy. We can meticulously observe how galaxies have evolved over immense periods of time. We meticulously look for those subtle, ancient fluctuations in the cosmic microwave background radiation. When we use all of this together, when we painstakingly extrapolate back to the earliest stages of the Big Bang using these multiple independent lines of evidence and 3 different types of instruments, or by looking at different aspects of the universe, the answers have consistently come back, roughly the same 13. 8 billion years, with an estimated accuracy of about 99%. It's a remarkable convergence, a testament to the power of scientific inquiry. But, as promised, there's another method, a different cosmic clock, which has gently thrown a bit of a spanner in the works, introducing a beautiful, intriguing paradox. And that method is to measure the age of individual stars. Certain types of stars, the most massive ones, are very short-lived, burning through their fuel incredibly quickly and going supernova in a matter of only a few million years. Others, the very smallest, faintest ones, could theoretically last for trillions of years, their lives stretching out beyond the current age of the universe itself. Not that we've seen one that old, for obvious reasons. In fact, meticulously following the evolutionary paths of stars, we haven't really seen any older than about 13.2 billion years old. This makes perfect sense. The first stars formed shortly after the Big Bang, and the most long-lived of those should still be quietly shining today. This means that long-lived stars that formed as matter was gently coalescing shortly after the Big Bang would certainly still be around today. Ancient beacons tracing the universe's earliest epochs. And this, friend, is where our intriguing companion, the Methuselah Star, gently enters our story. The Methuselah Star, formerly known as HD 140283, is a truly remarkable celestial object. It is classified as a metal-poor star, meaning it contains very few heavy elements beyond hydrogen and helium. This is a profound indicator of its extreme age, as the very first stars formed from the pristine, primordial hydrogen and helium created in the Big Bang, heavy elements were only forged later within stars themselves. So, a star with very few heavy elements is a very old star, incredibly rare, a true ancient relic. And most special of all, for our purposes, it is only about 200 light years away from us, a mere cosmic stone's throw in the grand scheme of things. This relative proximity means we can examine it in exquisite detail, gathering its subtle whispers with our most advanced instruments. Based on meticulous modeling of its evolution, its subtle changes in temperature, luminosity, and composition over billions of years, its estimated age is a staggering 14.5 billion years old, give or take about 800 million years. And here, friend, lies the beautiful, gentle paradox. If the universe itself is estimated to be 13.8 billion years old, how can a star within it be 14.5 billion years old? It's like finding a child who is older than their parent. This means the Methuselah Star, in its quiet, ancient wisdom, might have gently disproved the 13.8 billion year figure for the age of the universe, or at least challenged our precise understanding of it. So, do we really know how old the universe is? The answer, perhaps, is roughly, it wouldn't be surprising, and indeed, it's quite expected in the ever-evolving nature of science to see this figure subtly change as our technology improves, as our understanding becomes more refined. We have the James Webb Space Telescope, that magnificent successor to Hubble, already providing us with unprecedented views into the deep past and other future instruments on the horizon, all with specific mission objectives to peer even deeper into the universe's ancient history. These are truly exciting times, filled with the promise of new revelations. Although, in honest contemplation, I don't think we'll see this figure vary by more than about 1 billion years in either direction. The core methods are robust. The research is still in its very early days in terms of pinpointing such extreme precision, even if it has been a topic of profound research for a very long time. To be truly honest, it's profoundly impressive that we have gotten this far, that we can even contemplate such precise figures about the age of the cosmos. Who would have even thought, a few hundred years ago, that we could come up with any figure at all? It's a testament to the gentle persistence of human curiosity. All this exploration of cosmic time and ancient stars, may throw out more questions than it answered, leaving you with a soft hum of curiosity rather than firm conclusions. But that, friend, is science in a nutshell, the ongoing, beautiful search for truth, a journey filled with more questions than answers, but each question a new pathway to wonder. We have gently traced the grand timeline of the universe, pondering its immense age and the beautiful paradox of ancient stars. Now, let us shift our gaze from the sweeping scales of cosmic time to the intricate details captured by humanity's most patient and visionary eyes on the cosmos. Let us turn our attention to the Hubble Space Telescope, that marvel of human ingenuity which has been quietly orbiting our Earth for an astonishing 28 years. During this remarkable quarter century and beyond, it has diligently, patiently imaged some of the most spectacular sights within our own galaxy and far, far beyond, reaching into the deepest cosmic past. It is, truly, a wonder of technology, a testament to our boundless curiosity, and it has helped us to profoundly deepen our knowledge of the universe we inhabit, unveiling its secrets with breathtaking clarity. This includes understanding the many different types of stars that shimmer in our galaxy, each caught in various stages of their development, from fiery birth to luminous demise. In this quiet chapter, we are going to gently have a look at some of the most special and peculiar stars, some of the most exquisite cosmic phenomena that Hubble, with its unwavering gaze, has meticulously observed. And believe me, friend, when I softly tell you that some of these are simply breathtaking, truly awe-inspiring in their beauty and mystery, like distant, glittering jewels scattered across a velvet cloth. Our first destination is a place of profound creation, a cosmic nursery where new stars are gently being born. Let us contemplate HH 34, a designation that might sound technical, but which refers to an amazing site found nestled near the familiar Orion Nebula. This is a Herbig-Haro object, a designation given to the luminous, energetic jets of gas ejected from extremely young stars, stars that are still in the very earliest stages of their formation, quietly gathering material from their surroundings. Imagine a cosmic umbilical cord, feeding a nascent star. You can softly see the star itself here, still gracefully tucked inside this dense, swirling molecular cloud, a cocoon of gas and dust from which it is slowly emerging. The Orion Nebula is one of the closest HII nebulae, regions of ionized hydrogen, or star-forming regions, to us. This fortunate proximity means we can observe new stars in the profound process of being formed reasonably close up, witnessing the very beginnings of stellar life, like seeing a newborn creature take its first breath. The star, still in its energetic infancy, is powerfully releasing this extremely hot, focused jet of gas from one of its poles, a cosmic beacon cutting through the darkness. This jet speeds through space at hundreds, even thousands, of kilometers per second, an incredible velocity. Eventually, this energetic jet collides with colder, denser material in the surrounding space, heating it up and causing it to glow, which is precisely what you can see here at the bottom left of the image. For astronomical standards, this is a very short-lived event, a fleeting spectacle only lasting for a few thousand years before the jet dissipates and the star settles into its more mature life. It's a vivid, yet ephemeral snapshot of creation. Next, let us gently shift our gaze to more stars caught in the profound process of being formed, a cosmic tableau of stellar infancy. This is a region encompassing XZ Tauri and its neighboring stars, HL Tauri and V1213 Tauri. To me, this particular image, with its exquisite detail against the backdrop of a dark, brooding molecular cloud, is one of the most mind-blowing images Hubble has ever taken. It's a profound testament to the quiet, hidden processes of creation. Let's have a closer look at what's gently unfolding here. At the heart of this scene is XZ Tauri, a star system believed to contain two nascent stars, still gravitationally bound, separated by a distance roughly similar to that between our Sun and Pluto. For reasons still unknown to scientists, shrouded in cosmic mystery, these young stars have gracefully ejected a huge, expanding bubble of hot gas, shimmering delicately in the cosmic void. This bubble is expanding at a rapid, discernible rate, a majestic ballooning outwards, as evidenced by observations taken over the course of 5 years. It's a dynamic, evolving scene, a glimpse into stellar adolescence. Over here, nestled in the same cosmic neighborhood, is HL Tauri, another very young T Tauri star, a type of variable star still undergoing gravitational contraction and shedding its surrounding material. This star is particularly fascinating because it is surrounded by a magnificent, flat protoplanetary disk, a vast swirling pancake of gas and dust. This disk is the very material from which planets are likely still in the profound process of forming, a gentle cosmic construction site where future worlds are being sculpted from primordial dust. HL Tauri is also actively ejecting another powerful Herbig-Haro object, designated HH-150, a shimmering cosmic arrow shooting over in this direction, a sign of its energetic youth. And finally, in this remarkable trio, we find V1213 Tauri, a variable star with a spectacular, ethereal disk gracefully surrounding it. This disk is oriented almost perfectly side-on to us from our perspective on Earth, meaning it actually obscures our direct view of the star itself, like a cosmic veil. However, the star's reflected light, its gentle glow, brilliantly illuminates the surrounding gases and dust of the disk. From this system, yet another powerful Herbig-Haro object, HH-30 is dramatically shooting off in both directions away from the star, a symmetrical burst of cosmic energy. It's truly an amazing image, a profound glimpse into the bustling nurseries found near the Taurus constellation. Okay, let's allow our minds to savor just one more glimpse of a protostar, a star in its very earliest, nascent stage. This is HH-24. The star itself, the tiny, nascent ember, is once again skillfully hidden away by the comforting blanket of the molecular cloud, the dense, cold cocoon that surrounds it and from which it is continually being fed, drawing in its nourishment from the vast cosmic reservoir. But what is clearly evident, unmistakable and profoundly beautiful, is the bright, almost ethereal, lightsaber-like jet of gas being blasted away from the protostar in both directions, slicing through the cosmic darkness. It shares many visual similarities to the other Herbig-Haro objects we've already contemplated in this gentle journey. But the image itself is so utterly impressive, so visually striking. Nonetheless, this particular protostar, this quiet act of creation, is also found nestled near the familiar Orion Nebula, a testament to its prolific star-forming activity. Now, having witnessed the tumultuous yet beautiful beginnings of stellar life, let us gently move on to stars nearing the very end of their grand, luminous journeys. Our next focus is not the obvious, bright star you might initially see, but rather this dark, enigmatic spiral gracefully swirling next to it. This is LL Pegasi, and it presents one of the most perfect, geometrically stunning objects ever formed in the vastness of space. But what, precisely, is it? This astonishing spiral is actually a pre-planetary nebula. Imagine, if you will, a massive star, unseen behind all this shimmering dust in the very center, gently shedding some of its outer mass, like a cosmic serpent shedding its skin. This process occurs potentially just before it erupts into a full-fledged planetary nebula. The subtle, yet crucial difference between a pre-planetary nebula and a true planetary nebula lies in how they illuminate. A pre-planetary nebula, like LL Pegasi, is essentially a reflection nebula, meaning it is illuminated by the gentle light reflecting off the dust and gas that the central star has shed. In contrast, a fully developed planetary nebula consists of extremely hot, ionized atoms that produce their own light, glowing intrinsically with a vibrant luminescence. In the mesmerizing image of LL Pegasi, the material forming the spiral is observed to be moving at an astonishing speed of 50,000 kilometers per hour. And by combining this incredible speed with the meticulously measured distance between the spiral layers, astronomers have gently estimated that the central star system produces a new ring of ejected material roughly every 800 years. This precise, rhythmic pattern, this cosmic clockwork, is believed to be directly related to the profound fact that this is a binary star system. The orbital period of the two stars around each other, their intimate cosmic dance, is thought to also be approximately 800 years. This profound correlation strongly suggests that the mesmerizing spiral, this perfect cosmic geometry, is the direct result of the orbital motion between the two stars as one of them, the more massive partner, gently sheds its outer mass, painting a spiral across the heavens with each revolution. Our cosmic journey now takes us to another intriguing preplanetary nebula, known as HD 44179, affectionately nicknamed the Red Rectangle Nebula due to its unique, almost architectural, rectangular or X shape. This nebula is truly hard to observe from a ground-based telescope. as the Earth's turbulent atmosphere, like a shimmering veil, distorts its delicate light. This is one of those profound situations where having the Hubble Space Telescope, quietly orbiting high above the atmospheric interference, truly proves its invaluable worth, offering us an unobstructed, crystal-clear view into its mysteries. This pre-planetary nebula, with its perplexing, precise geometry, has really baffled scientists who don't yet fully understand the exact mechanics of how this precise, rectilinear structure formed. However, there is compelling evidence, subtle whispers from the data, that this unique shape is also due to another close binary star system. In this scenario, one of the stars, perhaps about the mass of our own sun, gently shed its mass in a structured way before it eventually transforms into a white dwarf. It is the remaining white dwarf, the hot, dense core, that will eventually radiate intense ultraviolet light, gently ionizing the ejected gas, causing it to glow brightly and become a fully fledged, luminous planetary nebula, shedding its reflective guise for an intrinsic glow. Let us now gently explore a completely different type of star, one that quietly pulses with a rhythmic beat, its brightness waxing and waning like a cosmic heart. This is RS Puppis, and the bright star at the very center of the image is our quiet focus. There is something profoundly unusual and incredibly beautiful about this particular star. It is a variable star known as a Cepheid variable. This means that its brightness doesn't remain constant. Instead, it varies dramatically, by a factor of 5, once every 40 days or so, in a precise, predictable rhythm. This rhythmic pulsation is a fundamental property of Cepheid variables, making them incredibly valuable as cosmic distance markers. Because this particular Cepheid star is surrounded by a beautiful, ethereal dust structure, a swirling veil of cosmic particles, we can actually observe the variable nature of its light through a phenomenon known as a light echo. Imagine dropping a pebble into a still pond and watching the ripples expand outwards. Light, though traveling incredibly fast, still takes a measurable amount of time to traverse astronomical distances. This means we can visually perceive the procession of light traveling away from the star, illuminating successive layers of the surrounding dust. As the star brightens and dims in its 40-day cycle, these pulses of light travel outward, creating visible rings of varying brightness. We see some rings that are subtly darker, reflecting moments when the star was dimmer, and other rings that are beautifully brighter, reflecting moments when the star majestically brightened. Hubble meticulously imaged RS Puppis over a 5-week period, and in the resulting time lapse, you can actually see this light echo, these shimmering rings gently pulsing outwards like the ripples from a cosmic breath. All in all, it's a ghostly yet profoundly beautiful image, a visual symphony of light and time. Our next cosmic wonder is A.G. Carini, another type of variable star, but one of truly immense scale. It is one of the brightest stars in our entire Milky Way galaxy, a colossal beacon of light. Because it is so extraordinarily bright, it is also incredibly short-lived, burning through its fuel at an astonishing rate. It is constantly, dramatically shedding its mass through powerful solar winds that rush outwards at an incredible speed of up to 7 million kilometers per hour. Imagine such a relentless, powerful outflow of stellar material. Much of the ethereal material surrounding this star, forming beautiful nebulae, is actually part of this ejected mass, further sculpted and shaped by the relentless force of its own solar winds. One day, in its distant, fiery future, this star will likely evolve into a Wolf-Rayet star, a particularly rare and luminous type of star that can be millions of times more luminous than our sun. However, even now. AG Carinae is so incredibly hot that it isn't directly visible to the naked eye. Much of its immense light output is in the ultraviolet spectrum, which is invisible to human eyes, requiring specialized instruments to observe its full, magnificent glory. Finally, for this chapter, let us venture outside the comforting boundaries of our own galaxy to witness a cataclysmic event of truly immense proportions. This is NGC 4993, a galaxy millions of light years away. So far, all the stars and nebulae we've gently looked at have been found within our own Milky Way galaxy. Observing individual stars outside our galaxy is incredibly hard, typically beyond the reach of our telescopes. But sometimes truly cataclysmic events happen in other galaxies, events so unbelievably grand, so profoundly energetic, that we can observe them even across millions of light years. And this is precisely what happened with NGC 4993, where something even more spectacular, even more profoundly dramatic than a supernova occurred a kilonova. Imagine the cosmic event that unfolded. In August 2017, the LIGO Laser Interferometer, Gravitational Wave Observatory, and Virgo observatories, those sensitive listeners to the universe's deepest tremors, quietly detected gravitational waves emanating from the titanic collision of two neutron stars. This was an unprecedented discovery, opening a new window into the universe. And within a mere 12 hours, a remarkably swift act of cosmic detective work, the precise source of these gravitational waves had been discovered in the galaxy NGC 4993. Considering it is so incredibly bright and evident, even from 140 million light years away, one can only begin to imagine what it would have been like to witness such an event from within the same galaxy. A cosmic spectacle of unimaginable power. These two incredibly dense neutron stars, after their long, spiraling dance, will have finally combined to form a black hole, the ultimate gravitational endpoint, and the resultant kilonova explosion was truly magnificent. Unlike a supernova, which is the explosion of a single star, a kilonova is born from the merger of two compact objects, like neutron stars. This event emitted an astonishing burst of electromagnetic radiation across every single frequency, from gentle radio waves to powerful gamma rays, painting the cosmos with its light. Intriguingly, it is now widely believed that the collision of neutron stars, these spectacular kilonovae, could be the primary source of the very heaviest elements in the universe, elements like gold and platinum. If that is indeed true, it gives your cherished jewelry a bit of a profound new perspective, doesn't it? A silent whisper of cosmic violence, transformed into shimmering beauty. We have gently witnessed the awe-inspiring birthplaces of stars and the cataclysmic, yet creatively powerful, mergers of neutron stars. Now, let us allow our minds to drift into another realm of cosmic wonder, a place of immense beauty and ceaseless activity, the Tarantula Nebula. This isn't just any nebula, it is a truly huge, profoundly impressive cloud of gas and dust, found nestled within the large Magellanic Cloud, a magnificent satellite galaxy gracefully orbiting our own Milky Way. Some might quietly argue that it isn't quite as classically pretty as some of the other nebulae we've gently explored so far, perhaps lacking the delicate, ethereal symmetry of others, but I must softly say, it certainly looks quite grand in its own right, a sprawling, vibrant tapestry of cosmic activity. But if it isn't just its visual charm that makes this nebula stand out, what truly defines it? What sets it apart from anything else we've looked at so far in our quiet cosmic journey? Well, we'll come back to that profound question. Let's first, for a moment, gently give you some context, helping our minds settle into its cosmic location. Imagine, if you will, our own Milky Way galaxy, that vast shimmering island of stars where we reside. Now, picture the large Magellanic Cloud, or LMC, the largest of the Milky Way's satellite galaxies, a smaller yet vibrant companion. And as you can softly see from cosmic maps, it is absolutely brimming with nebulae, each a testament to stellar activity. The one we're focusing on, the Tarantula Nebula, is the brightest and by far the biggest nebula in this entire galaxy. And it truly is bright. Incredibly so. I specifically chose this image because it still manages to show some of its exquisite details. Most other images I've encountered depict it as merely this brilliant, almost overexposed spot of light, its core shining with such intensity it washes out its intricate textures. It's so profoundly bright, in fact, that if this nebula were as close to us as the familiar Orion Nebula in our own Milky Way, it would astonishingly cast shadows at night. Imagine that a distant cloud of gas and dust, so luminous it could illuminate our Earth in the absence of the sun, a true second moon. Let's zoom in gently to find out precisely why. The Tarantula Nebula is currently undergoing a period of extreme, relentless star formation. It is a cosmic factory, churning out new stars at an astonishing rate. In fact, it holds the title of the most active star-forming region in the whole local cluster of galaxies, our immediate cosmic neighborhood. At its very heart, like a brilliant, bustling city center, lies a region of intensely concentrated stars known as NGC 2070. And within NGC 2070, nestled like a glittering diamond, is an even denser, more compact central concentration of stars, truly the powerhouse of the nebula, known as R136. It is this incredible star cluster that produces most of the immense energy, most of the blinding light, that makes this entire nebula so profoundly visible, so breathtakingly luminous. It's an incredibly massive cluster, containing an estimated 450,000 solar masses worth of stars within its relatively small confines. Imagine the sheer number of suns, the collective brilliance. Now, if you have ever, in your quiet moments of cosmic wondering, pondered what the most massive and brightest known star was, look no further. One of the stars residing in this very cluster. R136, a truly colossal beacon known as R136A1, is the most massive and brightest star ever recorded. Its statistics are truly mind-bending, almost beyond comprehension. It is a Wolf Rayet star, a rare and immensely luminous type of supergiant, weighing a staggering 315 times the mass of our Sun, and its luminosity, its sheer output of light, is an astonishing 8.7 million times greater than that of our own comforting Sun. It is also one of the hottest stars known, blazing with a surface temperature of 53,000 degrees Celsius. While it is the most massive star we know, it isn't the biggest in terms of physical size. Some red supergiants like Betelgeuse claim that title, although its actual size still dwarfs our Sun, almost beyond comparison. As is always the case with these incredibly massive, incredibly luminous stars, they are destined to be incredibly short-lived, burning through their fuel at a furious pace. R136A1 will almost certainly, in its distant, fiery future, become a black hole, collapsing into gravity's ultimate embrace. In the meantime, it is continuously shedding its immense mass through powerful solar winds, vast outflows of stellar material at a very, very fast rate. Since its birth, it's thought to have already lost a staggering 50 solar masses of material into space, a constant, powerful exhalation. Overall, the R136 star cluster itself is thought to be only about 2 million years old, a mere blink of an eye in cosmic timescales, still in its energetic infancy. It's currently gently merging with another close-by cluster, the two clusters together forming the grand tapestry of NGC 2070. You may not think that there are enough stars in this Hubble image to make up 450,000 solar masses, but remember, friend, these brilliant blue stars you see in this image are only the very brightest O-type stars in the cluster, those luminous giants that dominate its light. Beneath them lies a vast population of smaller, fainter stars, quietly contributing to the cluster's immense mass. Intriguingly, there is a star that truly belongs to this cluster, yet isn't found anywhere near its bustling heart. If we zoom out a bit, allowing our minds to encompass a wider view, you'll find this solitary star over here. It's called 30 Doradus 016. This young star, estimated to be only 1 to 2 million years old, may have traveled about 375 light years from its suspected home in the R136 star cluster, and it's still gracefully traveling, hurtling through space at an astonishing speed of about 400,000 kilometers per hour. But how did it get all the way out here, so far from its birthplace? The prevailing theory, a whispered possibility, is that it was once part of a binary star system within R136, then another even more massive star, a cosmic bully, entered the system, its powerful gravity disrupting the delicate balance and gravitationally kicking out the now homeless star, sending it hurtling into the vastness of space. These other stars, those cosmic bullies, would have had to have been incredibly massive, for 30 Doradus 016 itself is no minnow. It's a suspected 90 solar masses. It is now a lonely explorer, destined to travel the far reaches of the large Magellanic Cloud, a testament to the dynamic, sometimes violent nature of stellar interactions. Beyond the energetic youth of R136, there is another, older star cluster found in the Tarantula Nebula called Hodge 301. This cluster is roughly 20 million years old, making its stars significantly older, with some individual stars perhaps 10 times as old as those found in the youthful R136. This difference in age is crucial. Within Hodge 301, it is thought that there have been at least 40 stars that have already gone supernova, completing their dramatic life cycles, whereas in R136, due to its extreme youth, there have been none yet. This contrast highlights the relentless march of stellar evolution, and more stars within this older cluster are on the very verge of exploding in their own magnificent supernova. So watch this space, friend, for future cosmic fireworks. The original image we first looked at, that sprawling vista of the Tarantula Nebula, is actually found further away, still from the very center of the nebula, though it is undeniably still a vibrant part of it. This particular area is called NGC 2060, and it is located over here in the broader cosmic landscape. It is also a star cluster, though the stars here are much more loosely dispersed than in the dense cores of R136 and Hodge 301. In fact, these stars are no longer gravitationally bound to each other, a quiet sign of their dispersal. In a few million years, this stellar group will completely scatter, its members drifting into the wider galaxy. It's currently about 10 million years old, a gentle adolescent in cosmic terms, and there are some very interesting things found within this area. The first and quite profound detail I'll mention is that the whole of NGC 2060 is actually a supernova remnant, an expansive, shimmering bubble of gas and dust about 165 light years across. It's estimated that the original supernova explosion, the cosmic event that created this vast remnant, occurred approximately 4,000 to 5,000 years ago. And consistent with this theory, a pulsar neutron star, the incredibly dense, rapidly spinning core of the exploded star, is found precisely in this area. Here, roughly the same age as the supernova event itself. It's not really visible in normal light, as it primarily emits X-rays, which means you need a specialized X-ray telescope like Chandra to quietly glimpse its presence. And it sits right in the middle of this vast bubble, a silent, powerful heart. The bubble itself is, of course, the enduring supernova remnant, a testament to the immense power of its creation. This particular pulsar rotates exceptionally fast, completing a full spin once every 16 milliseconds. Imagine that dizzying speed. Intriguingly, this incredibly fast-spinning pulsar is not the fastest rotating star in this region. That incredible accolade, that distinction for cosmic speed, belongs to a peculiar object known as VFTS 102, a runaway blue supergiant. It is, in fact, the fastest rotating star that we know of anywhere in the universe, spinning at a dizzying speed of 2 million kilometers per hour. This is an astonishing 100 times faster than the rotational speed of our own sun. It spins so incredibly fast that the star itself is visibly flattened, like a cosmic pancake, with an equatorial disk of material gently extending outwards due to the immense centrifugal forces generated by its rapid spin. It is suspected that this runaway star, VFTS 102, was actually part of the same original binary system as the pulsar and would have played a profound, dramatic hand in its supernova explosion. Before the supernova, there would have been two massive blue stars orbiting one another in a close gravitational embrace. One of them, the more massive partner, would have evolved more quickly, transforming into a red supergiant. As it expanded dramatically, its outer layers would have begun to gently spill onto its companion star, feeding its mass and, crucially, speeding up the rotation of the other star, VFTS 102, to its astonishing current rate. Once the red supergiant finally exhausted its fuel and exploded in a supernova, the powerful asymmetrical blast would have ejected the other star, VFTS 102, at a tremendous speed into space, sending it hurtling away from its birthplace. VFTS 102 fits this model perfectly, as it is both spinning incredibly rapidly and simultaneously hurtling through space at immense velocity in relation to its stellar neighborhood. It's a profound tale of cosmic interaction, loss, and incredible speed. Zooming out further again, allowing our minds to encompass the grand vista, we are now gently getting to the very edge of the Tarantula Nebula. At its longest points, the Tarantula Nebula is an incredible 1,000 light-years across. That's a distance so vast it stretches the very limits of our comprehension. I already mentioned this nebula is the most active star-forming nebula known as an HII region in our entire local cluster of galaxies. But it is also, quite simply, the biggest. If it were as close to us as the Orion Nebula, it would be twice as big in our sky as the Big Dipper, that familiar constellation we know so well. And because it's so immensely bright, as we discussed earlier, it would even be visibly luminous during the day. Imagine a permanent, shimmering cloud in our daytime sky, a truly breathtaking sight. At the far edge of this magnificent nebula, perhaps its most remarkable visual spectacle awaits. It's called SN 1987A, and it is a supernova remnant. This particular remnant is considerably younger than any of the other supernova we've gently looked at so far. In fact, it's less than 30 years old, a mere infant in cosmic terms. The light from this supernova first hit Earth in 1987, reaching us after its 168,000-year journey from the Large Magellanic Cloud, and it was strikingly visible to the naked eye. It was the first supernova observed in centuries, since the 1600s, and uniquely, it was the only supernova observed in the modern era that we've had a close, detailed look at using modern-day telescopes like Hubble. When it exploded, it was a blue supergiant, which means it was only about 1/10 of the brightness of a red supergiant supernova. We hadn't had the chance to observe a blue supergiant supernova before, so it provided invaluable insights. I bet you're quietly wondering what these mysterious rings surrounding SN 1987A could possibly be. Well, they are the mass thrown off by the star itself through powerful stellar winds, gentle cosmic coughs and splutters from its innards, literally thousands of years before the supernova explosion actually occurred. The initial, brilliant flash from the explosion, the light wave expanding outwards, gently illuminated these pre-existing rings at first, making them glow. But then, when the supernova shockwave, a faster-moving, more energetic wave of debris from the explosion hit them a few years later. They lit up again, even more dramatically, due to the intense interaction between the shock wave and the existing ring material. SEN 1987A is now a true classic supernova remnant in the venerable vein of objects like Cassiopeia A, another famous supernova remnant. It is illuminated not solely by the initial explosion of the star, but by the continual powerful processes that occur between the expanding debris of the supernova and the surrounding interstellar material. This artist's illustration of SN 1987A, beautifully based on real observational data, reveals the cold, dense inner regions of the exploded star's remnant. This patch here, highlighted in red, indicates where tremendous amounts of dust were detected and meticulously imaged by the ALMA telescope, the very same one that observed Betelgeuse. It's within this dense, dusty heart that the leftover pulsar, the remnants of the star's core, could still be quietly hiding, waiting to be discovered. But because nothing has been definitively detected where the pulsar should be, another profound option remains that it didn't turn into a pulsar at all, but is actually now a fully formed black hole. The mystery, like the dust, gently swirls. We have journeyed far and wide through the cosmic tapestry, witnessing the birth and death of stars, the quiet mysteries of black hole mimics, and the dazzling spectacle of celestial explosions. As our final contemplation in this gentle exploration, let us now gather the threads of these wonders, bringing our thoughts to a soft conclusion. The Tarantula Nebula, that immense, vibrant cloud of gas and dust, remains one of the most remarkable places in our galactic neighborhood. Its sheer scale, a staggering 1,000 light-years across, dwarfs many other nebulae. Imagine that vastness, a cosmic canvas so immense that it would stretch twice the apparent size of the Big Dipper if placed as close as the Orion Nebula, and its brilliance, born from the ceaseless activity within, is so profound that it would astonishingly cast shadows on Earth at night. Were it closer, it is, undeniably, the most active star-forming region, an HII region, in our entire local cluster of galaxies, a true cosmic factory, perpetually churning out new suns. Within its sprawling embrace, we found the youthful, bustling heart of R136, a star cluster so dense and luminous, it alone powers much of the nebula's glow. Here, we marveled at R136A1, a true cosmic titan, the most massive and brightest star ever recorded, burning through its colossal fuel at an unimaginable rate. Destined for an ultimate dramatic collapse into a black hole, its very existence is a testament to the extremes of stellar life. And then, there was the intriguing tale of 30 Doradus 016, a runaway star, a cosmic wanderer kicked out from its birthplace, hurtling through space, a silent echo of violent gravitational interactions. Further, our gaze drifted to the older, more mature cluster of Hodge 301, a place where stars have already completed their fiery lives, leaving behind the silent whispers of at least 40 past supernovae. It's a testament to the relentless march of stellar evolution, where even the most luminous giants eventually fade. And within the broader expanse of NGC 2060, a supernova remnant stretching 165 light-years across, we encountered the incredibly dense, rapidly spinning heart of a pulsar neutron star, a cosmic lighthouse blinking silently in X-rays. Yet, even this incredibly fast spinner was outmatched by VFTS 102, the fastest rotating star we know, a blue supergiant flattened by its dizzying speed, a profound survivor of a dramatic binary interaction that likely involved the very supernova that birthed its pulsar companion. These are the dynamic, sometimes violent, interactions that sculpt the cosmic landscape. Finally, at the very edge of the Tarantula Nebula, we contemplated SN 1987A, a supernova remnant barely 30 years old, a recent cosmic explosion that graced our skies. It was the first supernova visible to the naked eye in centuries, offering an unprecedented opportunity for modern telescopes to study the aftermath of a star's death. Its mysterious rings, illuminated by the star's initial flash and then reignited by the powerful shockwave, painted a beautiful, evolving picture of stellar exhalations, and within its dusty, cold heart, the possibility lingers: is there a hidden pulsar, or did it too succumb to gravity's ultimate embrace, forming a black hole? The universe, in its quiet wisdom, still holds many secrets, many questions yet to be fully answered. These are but a few glimpses, a handful of stories from the vast, unending tapestry of the cosmos, from the gentle, life-giving glow of our sun to the theoretical whispers of gravastars, from the puzzling spin of Betelgeuse to the recurring brilliance of the blazed star, and from the grand timeline of the universe's age to the intricate, violent beauty captured by the Hubble Space Telescope. Each tells a story of profound forces, unimaginable scales, and the ceaseless dance of creation and destruction. This entire journey, this quiet contemplation, reminds us that the universe is not a static, unchanging backdrop, but a living, breathing entity, constantly evolving, constantly surprising. Even stars, which seem so eternal in their distant, shimmering brilliance, have astonishing life cycles that can include drastic changes, dramatic explosions, and profound transformations. Each nova, each supernova, each peculiar star observed provides a unique opportunity for astronomers to patiently gather data, to refine our understanding of stellar evolution, of binary star systems, and of the explosive yet creative stellar phenomena that shape the very cosmos we inhabit. This quiet exploration, this gentle invitation to wander through the immense, shimmering tapestry of the cosmos, is a reminder that we are part of something truly grand, something far beyond our immediate grasp. It's a space where you can let your thoughts drift freely among grand ideas, vast distances, and the gentle hum of existence. There's no pressure to find quick answers or solve complex equations, just the serene beauty of the unknown, the profound peace of quiet curiosity. As the echoes of these cosmic tales gently fade, allow your mind to quieten, to settle into a state of deep relaxation. Let the thoughts of distant stars, expanding nebulae, and the ancient whisper of the universe gently lull you, dissolving any tension, any lingering worries. There is no urgency here, just the soft rhythm of your breath and the vast, peaceful embrace of the cosmos. This is not medical advice and is not a substitute for professional medical advice or treatment. The purpose of this article is to provide entertainment and scientific exploration only.